Welcome to our channel. Today, we're diving into the incredible science behind our planet, Earth. From the mysterious depths of its oceans to the vast skies above, Earth is a wonder of nature and physics. Did you know that our atmosphere shields us from deadly cosmic radiation? Or that the planet's magnetic field works like an invisible armor? In this video, you'll discover mind-blowing facts about Earth's history, geology, climate, and the intricate systems that sustain life. Whether you're a curious mind or a science lover, get ready to explore the amazing truths of our home planet. Let's begin the journey. Amid the boundless expanse of the cosmos, one extraordinary planet stands as a haven for life: Earth. It seems as though our planet was tailor-made for us, providing water to drink, food to eat, and air to breathe. Earth is not just our home. It's our lifeline, sustaining every aspect of our existence. But what if I told you that 5 billion years ago, none of this existed? Where Earth now orbits, at the edge of the Milky Way, there was nothing more than a vast, swirling cloud of gas and dust. This is the incredible story of how that unremarkable cloud transformed into the vibrant, life-sustaining planet we call home. To understand the birth of Earth, we turn to experts like astronomer Tom Fleming. With the help of powerful telescopes at places like Kitt Peak in southern Arizona, astronomers have pieced together the fascinating puzzle of Earth's origins. It all starts with a molecular cloud, a colossal collection of gas and dust particles, no bigger than grains of sand or silicon. These clouds, like those captured by the Hubble Space Telescope, stretch hundreds of light-years across the galaxy. They're not like the clouds we see in the skies of Earth. They're ancient remnants, the ashes of long-dead stars. When the first generation of stars in the universe exhausted their fuel, they died in spectacular explosions known as supernovae. These violent events scattered heavy elements, iron, silicon, aluminum, and nickel, into the cosmos, enriching molecular clouds with the building blocks of new stars and planets. Gravity is the silent architect in this cosmic drama. The same force that pulls an apple to the ground on Earth also draws particles of dust and gas together in space. Over millions of years, gravity worked tirelessly, pulling the molecular cloud inward, compressing and heating it. As the cloud collapsed under its own gravity, something extraordinary happened. The immense pressure and motion within the cloud sparked the beginnings of a star at its core, a process mirrored in countless regions of the universe. And within this cosmic cradle, the seeds of planets began to form. Let's delve into this process further, starting with the forces at work within a collapsing gas cloud, and see how they shaped the birth of our planet. The story of Earth's creation is one of chaos, resilience, and ultimately, life. Astronomer Tom Fleming's demonstration of spinning with the LED balls vividly illustrates a crucial concept in the formation of planets. By increasing his rotational speed, as he pulls the balls closer to his body, Fleming mimics the behavior of a collapsing molecular cloud. What begins as a vast, slow-turning mass contracts under the force of gravity, causing it to spin faster and faster, a phenomenon called the conservation of angular momentum. In the depths of space, this simple yet profound principle transformed a sprawling cloud of gas and dust into our Sun and the surrounding planetary system. As the collapsing cloud spun faster, its center grew increasingly hot, igniting nuclear fusion and giving birth to our Sun. But not all the material was destined to become part of this blazing star. The outer regions of the spinning cloud flattened into a disk, a vast swirling structure of dust and gas that would become the cradle of the planets. Within this protoplanetary disk lay the seeds of Earth, though how these grains of dust managed to coalesce into a planet remained a mystery for centuries. The answer, as it turns out, came not from complex simulations or high-tech equipment, but from a curious experiment aboard the International Space Station in 2003. Astronaut Don Pettit, fascinated by the effects of microgravity, conducted a series of impromptu experiments. Among them, he filled a plastic bag with salt crystals, inflated it, and shook it gently. To his surprise, the tiny grains began clumping together, forming small aggregates that resembled dust bunnies. While it seemed like a simple curiosity at the time, this experiment inadvertently unlocked a key to planetary formation. When fellow astronaut Stan Love reviewed the footage, he immediately recognized its significance. In zero gravity, the salt grains behaved differently than they would on Earth, sticking together instead of remaining separate. Love realized that static electricity was at play, a phenomenon we see every day when a balloon sticks to a wall after being rubbed against hair. In the weightlessness of space, particles naturally gained slight electrical charges as they collided, causing them to cling together. This discovery shed light on the earliest stages of planetary formation, revealing how microscopic particles in the protoplanetary disk began to coalesce into larger and larger structures. Imagine the early solar system, a disk of swirling gas and dust, dotted with countless microscopic particles. Over time, these particles clumped together into larger aggregates, forming objects roughly the size of pebbles. As these pebbles collided and merged, they grew into boulders and eventually into planetesimals, objects about half a mile in diameter. These planetesimals had enough mass to exert a gravitational pull, allowing them to attract even more material from their surroundings. Like cosmic vacuum cleaners, they swept through the disk, collecting dust, gas, and smaller debris. Within a few million years, a mere blink of an eye in cosmic terms, these planetesimals grew into roughly 20 small planets orbiting the young sun in the inner solar system. The process was chaotic and violent, with frequent collisions between these embryonic worlds. The competition for material in the disk was fierce, and only a few of these early planets would survive the relentless impacts and gravitational interactions. One of the survivors was the young Earth. Around 4.5 billion years ago, it was a molten world, its surface a sea of liquid rock. The intense heat came from two main sources: the kinetic energy released during countless collisions, and the radioactive decay of unstable elements within the planet. Despite its fiery beginnings, Earth was on a path toward becoming a habitable world. During this time, the young Earth experienced its most defining collision. A Mars-sized object, now referred to as Theia, slammed into the Earth with unimaginable force. The impact ejected a massive amount of material into space, which eventually coalesced to form the Moon. This cataclysmic event not only shaped the Earth's future, but also stabilized its rotation, giving us consistent seasons and tides, factors crucial for the development of life. As the planet cooled, a thin crust formed over its molten interior. Volcanic activity was rampant, spewing gases into the atmosphere and creating a toxic mix of carbon dioxide, ammonia, and methane. There was no oxygen yet, and the surface was still too hostile for life. But deep within this turbulent environment, water began to appear. Some of it likely came from the cooling process of the Earth's interior, while the rest may have been delivered by icy comets and asteroids bombarding the planet. With water came the potential for life. Pools and oceans began to form, creating the conditions necessary for the first chemical reactions that would lead to life's emergence. At this stage, The Earth was unrecognizable compared to the lush green planet we know today, but the foundation was set. To fully grasp the magnitude of Earth's transformation, we can compress its 4.5 billion-year history into 12 hours on a clock. The story of our planet begins at noon, with its violent birth and fiery infancy. By 1230, the surface begins to cool, and the first oceans appear. By 1 o'clock, the building blocks of life are present. It would take billions of years, hours on this cosmic clock, before complex life forms, and even longer for humanity to arrive. This is only the beginning of Earth's story, a tale of resilience, chaos, and unimaginable transformation. What lies ahead in this narrative is the journey from this molten, lifeless world to the thriving, complex biosphere we now call home. The next chapter in Earth's story was one of chaos and violence. The young solar system was a battlefield, with around 20 protoplanets locked in a gravitational dance. Their orbits were unstable, and collisions were inevitable. When these massive objects collided, their combined energy was enough to melt rock and reshape the survivors. Over time, these brutal encounters reduced the inner solar system to just a handful of planets: Venus, Mercury, Mars, and Earth. Astronomers estimate that the Earth grew to its current size within roughly 30 million years, a blink of an eye in cosmic terms. By this point in our story, we are only 5 minutes into the metaphorical clock of Earth's evolution. But what was this early Earth like? Could it have supported life, or even briefly accommodated a human visitor? The answer is an emphatic no. Early Earth was a furnace. The immense energy released by planetary collisions had left the surface at a searing 8,500 degrees Fahrenheit, hotter than 5 cremation furnaces combined. Any human attempting to set foot here would vanish in an instant, reduced to a puff of steam and ash. As the planet began to cool, a new threat emerged: a relentless storm of charged particles from the young sun. This was no ordinary solar breeze, but a hurricane of radiation traveling at millions of miles per hour. It was a storm so intense that it could have erased all chances of life on Earth before it even began. 4.5 billion years ago, the Sun was a young star, volatile and unpredictable. It unleashed powerful solar winds, streams of energetic particles traveling at immense speeds. Today, scientists like those at the Space Environment Center in Boulder, Colorado, monitor such solar activity around the clock. Space weather is extreme. Even a gentle breeze from the sun can reach speeds of 200 miles per second, with temperatures as high as 8,000 degrees Fahrenheit. These conditions highlight the sun's raw power and its potential to cause harm. Rodney Derrick, a space scientist, explains the danger. The sun is essentially a large explosion, constantly releasing energetic particles. These particles, known as solar wind, pose a lethal threat to astronauts and can wreak havoc on planets. When the charged particles collide with a planet's atmosphere, they can strip it away, leaving the surface exposed to the harshness of space. Mars serves as a grim reminder of what might have happened to Earth. Over millions of years, the relentless solar wind swept away Mars's once thick atmosphere. Today, it is a barren, frozen world, unable to support liquid water on its surface or provide breathable air. Earth could easily have suffered the same fate, but it didn't. Why? The answer lies deep within our planet's history and its very structure. During Earth's formation, the colossal impacts and gravitational compression generated immense heat. As the young planet melted, its materials began to separate based on density. Lighter elements, such as silicates, floated to the surface, forming the crust and mantle. Heavier elements, including vast quantities of iron, sank toward the planet's core. This process, known as differentiation, shaped the Earth into distinct layers and gave rise to its most crucial feature, the molten iron core. This core became Earth's invisible shield against the sun's deadly radiation. As molten iron churned in the planet's interior, it generated electric currents that, in turn, created Earth's magnetic field, a phenomenon known as the geodynamo. This magnetic field acts as a protective bubble, deflecting most of the solar wind and preventing it from stripping away our atmosphere. At the University of Maryland, researcher Dan Lathrop studies the mysteries of Earth's core using scale models that replicate its dynamics. The Earth's core operates like a dynamo, he explains. Currents in the liquid iron generate magnetic fields, which then protect the planet. This magnetic field, though invisible, has been one of the most crucial factors in Earth's ability to sustain life. Without this iron core and the magnetic field it produces, Earth might have become a lifeless rock like Mars. The atmosphere, so vital for moderating temperature and sustaining life, would have been stripped away, leaving our planet uninhabitable. Instead, the Earth's magnetic field deflects solar winds and traps harmful radiation in belts far above the surface, ensuring that life has the opportunity to evolve and thrive. As the Earth's magnetic shield took shape, it set the stage for a planet capable of sustaining life. The intense heat from its formation gradually dissipated, and the surface began to stabilize. This was a pivotal moment in Earth's evolution, a transition from chaos to the possibility of life. Yet, the journey was far from over. The young planet still had to face other trials before it could transform into the vibrant, life-filled world we know today. The story of Earth's resilience continues, as each chapter in its history builds upon the last, laying the groundwork for the development of life. From the fiery crucible of its formation to the magnetic shield protecting its fragile atmosphere, Earth's journey is one of survival against the odds. Dan Lathrop's research has shed light on the crucial role of Earth's spinning core in generating the magnetic shield that surrounds our planet. This shield, known as the magnetosphere, protects Earth from the relentless bombardment of solar wind. Using a simple yet effective demonstration, Lathrop illustrates how magnetic fields are created. By sprinkling iron filings around a coil of wire and connecting it to a power supply, the filings align along invisible magnetic field lines. This small-scale experiment mirrors what happens deep within the Earth, where the molten iron core acts as a natural dynamo, producing a magnetic field that defines the planet's north and south poles and extends far into space. The magnetosphere is Earth's first line of defense against the charged particles from the Sun. When these particles reach our planet, the magnetic field redirects most of them away, ensuring the atmosphere remains intact. However, some particles manage to penetrate this barrier near the poles, where they collide with atmospheric molecules to create breathtaking displays of light. The aurora borealis and aurora australis, commonly known as the northern and southern lights. The moon also became an integral part of Earth's story, shaping tides, seasons, and even the rhythms of life on the planet. Its presence is a constant reminder of the chaotic, violent processes that forged our solar system. The story of Earth and the Moon is one of cosmic resilience and transformation. From a fiery collision came not only the stability that Earth needed, but also a satellite that has remained our companion for billions of years. The moon's quiet glow in the night sky tells a tale of destruction and creation, a testament to the forces that shape the planet we call home. And as Earth cooled and evolved, the next chapter in its story would see the first stirrings of life in an environment still far from the one we know today. In 1963, the United States embarked on one of the most ambitious scientific endeavors in history, the Apollo program. Among its goals was to unravel the mystery of the Moon's origin. Between 1969 and 1972, American astronauts made 6 journeys to the Moon, where they conducted experiments, tested the limits of human exploration, and brought back 840 pounds of lunar rock for analysis. These lunar samples held vital clues about the Moon's formation. When scientists examined the rocks, they discovered something puzzling. The rocks were incredibly dry, as though they had been exposed to intense heat. This finding contradicted earlier theories about the Moon's origins and posed a significant challenge to existing explanations. Any new hypothesis about the Moon's creation would need to account for this unique characteristic. In the 1990s, planetary scientist Robin Canup sought to tackle this mystery using advanced supercomputer simulations. She tested a groundbreaking hypothesis. What if the Moon was born from a catastrophic collision between the young Earth and another massive planet? Her simulations offered stunning insights into this ancient event. Canup's model depicted a Mars-sized object, dubbed Theia, hurtling toward the proto-Earth at a speed of 7 miles per second. Theia struck Earth at an oblique angle, creating a glancing impact of unimaginable energy. The collision vaporized vast amounts of rock, melting the entire planet and ejecting an enormous arm of debris into space. This material didn't scatter aimlessly. Instead, much of it coalesced into a dense orbiting disk of molten rock and gas. The simulation revealed the sequence of events that followed. Theia's core likely merged with Earth's, while the outer layers of both planets were hurled into space. As the debris orbited the Earth, gravitational forces caused some of it to clump together. Over time, these clumps grew, eventually forming the Moon. This process, known as accretion, gave the Moon its dry and heat-altered composition, consistent with the findings from Apollo's lunar samples. The collision with Theia wasn't just a defining moment for the Moon. It also reshaped Earth itself. The impact melted the planet, creating the molten state that allowed the heavier elements to sink to the core and the lighter elements to rise to the surface. This event also set the stage for Earth's stabilization. The Moon's gravitational pull slowed Earth's rotation and created tides, laying the groundwork for the predictable environmental cycles crucial to the development of life billions of years later. Scientists are gradually piecing together the puzzle of Earth's water origins. A major breakthrough came in January 2005 with the launch of NASA's Deep Impact spacecraft, an ambitious mission designed to probe the enigmatic nature of comets. Its target was Tempel 1, a comet located 270 million miles away. The plan? To send an 800-pound copper impactor hurtling into the comet's surface at an incredible speed to uncover its secrets. For centuries, comets have been central to the theory that water was delivered to Earth from space. Their icy composition and the pockmarked surface of the Moon, scarred by countless impacts, suggested that Earth, too, must have been bombarded by similar objects during its history. Unlike the Moon, however, Earth's dynamic geology has erased the evidence of these early collisions. Still, many scientists believed comets carried water in the form of ice and played a crucial role in delivering it to Earth. The Deep Impact mission marked the first time humanity would attempt to probe beneath the surface of a comet to test this idea. On July 4, 2005, NASA scientists anxiously monitored the spacecraft as its impactor closed in on Tempel 1 at 23,000 miles per hour. When the collision occurred, it generated a massive explosion, scattering debris into space, a spectacle captured by telescopes around the world. The analysis of the material ejected from the comet confirmed the presence of water. But while this supported the theory that comets contain significant amounts of ice, the story didn't end there. Using advanced radio telescopes, astronomers examined the water vapor trails of several comets to determine whether their water matched the unique chemical signature of Earth's oceans. The results were surprising and disappointing. The isotopic composition of the water in all three comets analyzed so far does not align with Earth's water. This discrepancy has cast doubt on the comet theory as the primary source of Earth's water. However, the failure of the comet hypothesis has given rise to a new, exciting idea. A critical clue emerged on January 18, 2000, when a brilliant meteorite streaked across the skies of Western Canada before shattering over Tagish Lake in British Columbia. Witnesses captured the trail left by the meteorite, and scientists quickly recovered the frozen fragments from the lake. These pieces, preserved by the icy environment, represented some of the best preserved meteorites ever studied. Dr. Michael Zolensky, a space scientist at NASA, examined one of these fragments at the Johnson Space Center in Houston. Remarkably, despite the extreme heat generated by friction during its descent through Earth's atmosphere, the meteorite remained largely undamaged. Zolensky explained that meteorites, cold-soaked in space for millions of years, only heat superficially during atmospheric entry. The intense heat affects only the outermost layers for a few seconds, leaving the interior largely untouched. This particular meteorite, thanks to its fragile structure and the frozen lake where it landed, remained intact long enough for scientists to analyze its contents. If it had fallen anywhere else, it likely would have disintegrated into dust within days, Zolensky noted. Inside, they discovered a treasure trove of information. Around 20% of the meteorite's weight was water, trapped within clay minerals that formed in the cold depths of space. This was an extraordinary finding. A single meteorite carried significant amounts of water. Astronomers traced the meteorite's trajectory and identified its origin in the outer reaches of the asteroid belt, a region known to harbor icy bodies. Unlike comets, these asteroids orbit closer to Earth and may have served as a more accessible source of water. The composition of water in meteorites, like the one from Tagish Lake, closely resembles that of Earth's oceans, making them a compelling candidate for the source of Earth's water. This discovery suggests that the asteroid belt, rather than distant comets, may have been the primary supplier of water to the early Earth. During the chaotic period of planetary formation, countless meteorites likely bombarded Earth, delivering not only water, but also organic molecules, the building blocks of life. This new evidence has shifted the focus of scientists studying the origins of Earth's water and underscores the role of asteroids in shaping our planet's history. As we delve deeper into Earth's past, the story of its transformation continues to unfold. With water delivered and oceans forming, the stage was set for the next great leap, the development of an atmosphere capable of sustaining life. From a dry, molten wasteland to a planet rich in water, Earth was evolving into a world where life could begin. If you observe asteroids through telescopes, a fascinating trend emerges. The farther they are from the Sun, the more water they contain. This observation has led astronomers to hypothesize that asteroids from the outer regions of the asteroid belt were responsible for delivering water to Earth. In a torrential bombardment of meteorites, these space travelers may have brought the water that now forms our oceans. But what triggered this extraordinary shower of asteroids? The answer lies with the solar system's largest planet, Jupiter. With its immense mass and powerful gravitational pull, Jupiter's influence has been both a sculptor and a disruptor in the solar system. In the distant past, its gravity disturbed the orbits of thousands of asteroids, pulling them out of their stable circular paths into chaotic elliptical trajectories that crossed Earth's orbit. The result? A violent era of impacts as these asteroids collided with Earth. As each asteroid slammed into the planet, it released water trapped within its minerals. Impact by impact, explosion by explosion, this water escaped and began to accumulate, forming the first oceans. While scientists once believed it took hundreds of millions of years for Earth to acquire its water, more recent evidence suggests this process happened much faster, on a geological timescale, almost in the blink of an eye. A breakthrough came from the work of geologist Stephen Moisish, who conducted groundbreaking research in Boulder, Colorado. Moisish analyzed some of the oldest rocks on Earth, meticulously grinding them down to extract microscopic crystals known as zircons. These tiny, incredibly resilient minerals are nearly indestructible and serve as time capsules, preserving the conditions of the Earth's early surface. Using an ion microprobe to analyze the oxygen composition within the zircons, Moisish made a startling discovery. These crystals had formed from rocks that could only exist in the presence of water. This finding was a revelation. What was startling, exciting, fun, Moisish remarked, was that these zircons showed not only that things on the Earth's surface had stabilized to within normal conditions, but that water was present. And water was present everywhere. The zircons were dated to approximately 4.4 billion years ago, suggesting that Earth's water arrived remarkably early, within just 150 million years of the planet's formation. On the metaphorical 12-hour clock of Earth's history, this means that water appeared just 25 minutes after the clock began ticking. Such a rapid arrival of water fundamentally reshaped the young Earth, transforming it from a barren wasteland to a world teeming with oceans. However, Earth's early appearance would have been vastly different from what we see today. The oceans were rich in dissolved iron, much of it brought to the surface by hydrothermal vents, giving the water a greenish hue. The atmosphere, thick with nitrogen, carbon dioxide, and methane, cast a reddish tint across the sky. This environment, while hostile by modern standards, was a significant step closer to habitability. By this time, the land had cooled to a temperature that could potentially support life, and water was plentiful. Yet one critical ingredient for life as we know it was still missing: oxygen. The Earth's atmosphere lacked even a trace of this vital gas. Without oxygen to breathe, no complex life could exist. The planet was on the brink of transformation, but a monumental change was still required to create the conditions necessary for life to flourish. The next chapter in Earth's story would see the rise of oxygen, a phenomenon that would revolutionize the planet and set the stage for the explosion of life to come. Surviving on the early Earth was impossible for humans. 500 million years after its formation, the Earth had cooled significantly and was blanketed with oceans. But the atmosphere was still devoid of oxygen, a critical component for the existence of animals, humans, and most complex life. The Earth, while evolving, was not yet ready to host the diverse forms of life we know today. One scientist exploring the origins of Earth's oxygen is geologist Martin van Kranendonk. His journey led him to Shark Bay on Australia's west coast, a UNESCO World Heritage Site teeming with seagrass, dugongs, and dolphins. But van Kranendonk's interest lies not in these modern creatures, but in much older life forms, the stromatolites. These ancient, living structures have been growing in Shark Bay for about 10,000 years, since the end of the last ice age. As the sea level rose, these stromatolites reached their current form, providing a window into Earth's ancient biological processes. Stromatolites are relatively simple organisms. They exist as short pillars or flat mats, composed of blue-green bacteria, also known as cyanobacteria, intermingled with silt. Despite their simplicity, these structures played a monumental role in Earth's history. Cyanobacteria are among the earliest organisms to perform photosynthesis, using sunlight to convert carbon dioxide into oxygen. This process, over billions of years, transformed the Earth's atmosphere, making it hospitable to complex life. It's because of this oxygen production, Van Kranendonk explains, that we have the planet Earth as we know it today, a world where humans, animals, and plants can thrive. But Shark Bay's modern stromatolites are only part of the story. To understand their ancient origins, Van Kranendonk traveled over 1,000 miles north to the Pilbara region, one of Earth's oldest landscapes. The Pilbara feels like stepping into a time machine, transporting visitors back to Earth's earliest days. Hidden within this remote region lies one of the most extraordinary discoveries in the history of science: the oldest fossils ever found. These fossils, secreted away to protect their fragile state, are the ancestors of the stromatolites in Shark Bay. They are remnants of the earliest known life on Earth, dating back 3.5 billion years. Just 1 billion years after the planet's formation. Van Kranendonk reflects on the significance of these fossils. What's remarkable about this outcrop in the Pilbara is that it contains the oldest evidence for life on Earth. We're looking at our great-great-great-great-great-great-grandfathers and grandmothers. These ancient fossilized stromatolites are 15 times older than the dinosaurs, representing life at its most primitive yet profoundly impactful stage. Although the exact origins of life remain a mystery, these fossils suggest that life emerged remarkably quickly after Earth's formation. On the 12-hour clock of Earth's history, stromatolites appeared at approximately 20 minutes to 3. These early cyanobacteria began the slow but transformative process of oxygenating the atmosphere. Over billions of years, this shift allowed for the evolution of more complex life forms, eventually leading to humanity. The stromatolites in the Pilbara reveal an extraordinary truth: life's tenacity and its ability to shape an entire planet. These simple organisms initiated a chain reaction that would culminate in the rich biodiversity we see today. While Earth was still far from resembling the modern world, these early life forms laid the foundation for everything that followed, fundamentally altering the planet and setting the stage for the evolution of complex ecosystems. 3.5 billion years ago, stromatolites began producing oxygen through photosynthesis, seemingly ready to transform the Earth's atmosphere. Yet, for the next billion years, the oxygen levels in the air barely changed. The mystery of the missing oxygen lies hidden in the ancient rocks of Karijini National Park in Australia. These rocks, known as banded iron formations, hold the key to understanding why the atmosphere remained oxygen-poor for so long. Geologists believe these formations owe their existence to stromatolites and a unique set of conditions in Earth's early history. These banded iron formations, explains a geologist, are the product of microbial activity in ancient oceans. They began forming around 2.5 billion years ago, when the Earth was still very young. In those early days, Earth's oceans were rich with dissolved iron. As stromatolites bubbled oxygen into the water, it reacted with the iron, creating iron oxide, essentially rust. This chemical process can be demonstrated in a simple experiment. A flask of water containing iron, similar in color to the early oceans, is pumped with oxygen. The oxygen reacts with the iron, forming rust, which then precipitates to the bottom. For over 1 billion years, the iron in Earth's oceans consumed nearly all the oxygen that stromatolites produced. The rust settled to the ocean floor, forming layers that would eventually harden into rock. These banded iron formations locked away enormous amounts of oxygen, estimated to be more than 20 times the amount currently in Earth's atmosphere. The formation of these rocks was a slow process, spanning eons. On the 12-hour clock representing Earth's history, the planet formed in the first 8 minutes. By the 25-minute mark, it had cooled and collected water. But it wasn't until nearly 5 hours later, after most of the iron in the oceans had been removed and stored in rocks, that oxygen levels in the atmosphere began to rise. This critical shift happened around 2.5 billion years ago, triggering what scientists call the Great Oxidation Event. Over the next 2 billion years, oxygen levels steadily increased, creating an atmosphere capable of supporting complex life. By 500 million years ago, oxygen reached the levels necessary for animals to thrive. At this point in Earth's history, the planet had water to drink, air to breathe, and temperatures that could support life. If humans could travel back to this time, survival would finally be possible. Yet, life on Earth was still in its infancy. The first animals were only beginning to emerge, and humans were still billions of years away. As our story approaches its conclusion, 11 hours have now passed on the Earth's clock. The remaining minutes encapsulate dramatic events that shaped life as we know it. At 37 minutes to midnight, dinosaurs appear, dominating the planet for millions of years. At 10 minutes to midnight, they are wiped out by a catastrophic event, likely an asteroid impact. Finally, at 19 seconds to midnight, the first humans step onto the stage. It has taken over 4 billion years, but from a chaotic cloud of gas and dust, nature has forged the only safe haven we know in the universe, Earth. This remarkable journey reminds us how rare and precious our planet truly is. A unique home carved from the chaos of the cosmos. Our atmosphere. As the Earth continued its transformation, it developed one of its most essential features, the atmosphere. This thin layer of gases surrounding the planet became both a shield and a cradle for life, moderating temperatures, protecting the surface from harmful radiation, and eventually providing the oxygen that sustains all complex organisms. But how did this atmosphere form? In the cold, unforgiving expanse of space, where hostile planets and a freezing vacuum dominate, Earth stands as a rare oasis of life. What makes this possible is our atmosphere, a remarkable blanket of gas that insulates, protects, and sustains all living things. This invisible shield doesn't just provide air to breathe. It carries water across the globe, buffers against deadly cosmic radiation, and shields us from impacts that would obliterate life. It's time to uncover the layers of wonder that make our atmosphere essential. Down on Earth's surface, we rarely give much thought to the air we breathe. It's unseen, untouchable, and often taken for granted. Yet this thin veil of gases is all that stands between us and the deadly vacuum of space. As one scientist aptly puts it, our atmosphere is more than air. It's our shield, our lifeline. The atmosphere is divided into 5 distinct layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer becomes thinner and less dense as you ascend, extending for miles above our heads. The exact boundary of the atmosphere depends on interpretation. Some scientists claim it ends at 300 miles above Earth, while others argue it extends into interplanetary space, blending into the region surrounding Mars. Humans live within the troposphere, the closest layer to Earth's surface. Here, the air is thickest and the pressure is greatest, perfectly suited for our biology. Our metabolism, our very chemistry, one researcher explains, is intricately shaped by the conditions of this layer. Yet to truly appreciate the atmosphere's complexity and marvel at its role, we must rise through its layers, from the Earth's surface to the edge of space. On August 16, 1960, Colonel Joseph Kittinger prepared for a record-breaking journey that would take him to the upper reaches of the atmosphere, a world above 99% of Earth's air. This was not an ordinary adventure. It was a groundbreaking military mission to test the limits of the human body under extreme conditions. Kittinger's jump would provide critical data for the burgeoning space race and future high-altitude aviators. The mission relied on a simple but effective vehicle, a helium balloon tethered to an open-sided gondola. It was just an open gondola, Kittinger recalled. A space platform, an elevator as I called it. At 5:30 a.m., after meticulous preparations, Kittinger boarded the gondola. My crew chief asked, "Are you ready?" I said, "I'm ready, let's go." The ascent was smooth, and the balloon quickly rose into the sky. Within 30 minutes, Kittinger reached 29,000 feet, the middle of the troposphere. At this altitude, the air was so thin that each breath contained only a third of the oxygen available at sea level. Breathing from gas bottles connected to his sealed helmet, Kittinger pressed on. The journey to the jump point was far from over. Climbing at 1,000 feet per minute, he ascended through increasingly thin air. By the time he reached 40,000 feet, the pressure suit surrounding his body began to inflate, a reassuring sign that it was functioning properly. Yet, there was a problem. The glove covering his right hand wasn't sealed. I had an option to report the issue, Kittinger later admitted, but I knew they'd abort the mission. I didn't want to risk losing the chance to complete the flight. Kittinger chose to continue. The balloon rose steadily, eventually reaching 102,800 feet, a record-breaking altitude in the mid-stratosphere. At this height, the temperature had plunged to 67 degrees below zero, and the air pressure was less than 1/100th of what it was at sea level. For an unprotected human, this environment would be lethal within seconds. After 89 minutes of ascent, the balloon stalled, signaling the end of Kittinger's climb. It was time to begin his journey back to Earth. Standing at the edge of the gondola, Kittinger was ready. I had made this jump 1,000 times in my mind, he said. Every step, every movement, I had rehearsed over and over. Before stepping off, Kittinger offered a silent prayer and activated the onboard cameras. Then, with a small hop, he leaped from the gondola into the void. In an instant, he was free-falling toward Earth. During the descent, Kittinger reached speeds of over 600 miles per hour, plummeting through the stratosphere. His specialized suit protected him from the frigid temperatures and the crushing forces of acceleration. As he descended, the atmosphere gradually thickened, slowing his fall and cushioning the final leg of his journey. When Kittinger finally landed, he had completed one of the most extraordinary feats in human history. His leap from the stratosphere demonstrated not only the resilience of the human body, but also the incredible role of the atmosphere in protecting life. Without it, Earth would be as lifeless as the moon, and journeys like Kittinger's would be unthinkable. The story of our atmosphere is a testament to its power and significance. It is more than just air, it is the invisible force that has shaped our planet and made life possible. As we continue to explore its layers and uncover its secrets, we are reminded of its profound importance to our existence. As Colonel Joseph Kittinger plunged through the stratosphere, he was struck by an extraordinary realization. You can't tell that you're going fast. You can't tell anything, he recalled. Gazing upward, he saw the balloon that had carried him appear to shoot into space. Then it hit him. The balloon wasn't moving. It was Kittinger, hurtling toward Earth at a breathtaking speed. For 16 miles, he fell through the thin air, which provided almost no resistance. At his peak, Kittinger reached an astonishing speed of 614 miles per hour, nearing the speed of sound. After a record-breaking freefall lasting 4 minutes and 36 seconds, he deployed his main parachute, drifting safely to the desert floor below. "We were just elated," Kittinger reflected after his successful descent. "There were a lot of people who said we couldn't do it, and we proved that we could." His mission wasn't just a testament to human endurance and ingenuity. It also offered a rare glimpse into the incredible atmosphere that makes life on Earth possible. For Kittinger, returning to the ground felt like a blessing. It was a relief to be back on the planet we love so much, a planet with an atmosphere we can live in daily. Kittinger's record-breaking jump underscored the indispensable role of Earth's atmosphere, a mix of gases that we often take for granted. This thin veil surrounding our planet doesn't just provide air to breathe. It regulates temperature, protects us from harmful radiation, and enables life to thrive. Astronomer David Grinspoon reminds us of the rarity of Earth's atmosphere. "The more we learn about planets," he explains, "the more we realize that they're all individuals. As far as we know now, Earth's atmosphere is completely unique." Indeed, explorations of our solar system have revealed just how unusual Earth truly is. From telescopes to space probes, scientists have uncovered a vast diversity of atmospheres, none quite like ours. On icy Uranus and Neptune, near-frozen gases sweep across their surfaces in unrelenting winds. Mercury, scorched by the sun, has no real atmosphere to speak of. Standing on its surface would feel like floating in outer space. In stark contrast, Jupiter and Saturn are colossal gas giants with atmospheres so thick and deep they lack any discernible solid surface. Unlike Earth, Grinspoon explains, Jupiter doesn't really have a ground you could stand on. It's just a massive gas ball. Among Earth's planetary neighbors, only Venus shares a thick atmosphere and rocky surface. But despite these similarities, Venus is a hostile, alien world. Dr. David Crisp, who has spent decades studying Venus's atmosphere, paints a chilling picture of its surface. Imagine standing on Venus. The pressure is so immense it could crush a nuclear submarine. It's about 90 times the pressure of Earth's surface. And the heat? Venus's surface temperature soars to a staggering 900 degrees Fahrenheit, hot enough to melt lead. Its clouds, drifting lazily overhead, are composed not of water vapor, but concentrated sulfuric acid. For humans, Venus's environment would be instantly fatal. Venus is a cautionary tale of how extreme an atmosphere can become. Yet the real mystery isn't why Venus is so inhospitable. It's why Earth avoided the same fate. Earth and Venus are essentially twins, Crisp explains. They're nearly the same size and located close together in the solar system. Yet, their environments evolved in dramatically different ways. Understanding why these two planets, so similar in their origins, took such divergent paths has become one of science's most compelling questions. While Venus became a furnace, Earth developed a stable, life-supporting atmosphere. The key to this mystery lies in exploring the unique processes that shaped Earth's environment, including the role of water, the magnetic field, and the delicate balance of greenhouse gases. Earth's atmosphere is not only unique, but also fragile. As we study the extremes of other planets, we gain a deeper appreciation for the conditions that make Earth habitable. With each discovery, we are reminded that our atmosphere is a rare and precious phenomenon, a masterpiece shaped by billions of years of evolution. To uncover the secrets of how Earth retained its perfect atmosphere while Venus turned into a nightmare, we must delve deeper into the history of these two planets. Only then can we truly understand what makes our home a sanctuary for life. To uncover the origins of Earth's atmosphere, we must journey back 4.2 billion years to the very birth of the solar system. In this chaotic era, immense quantities of gas and dust orbited the Sun, gradually coalescing into the planets we know today. While Jupiter and Saturn grew into massive gas giants, Earth formed a molten core, with gases bubbling up from its fiery surface to create its first atmosphere. Unlike the lightweight gases of hydrogen and helium, which escaped into space, Earth's gravity was strong enough to retain these heavier gases. But this fledgling atmosphere faced an immediate and formidable threat: the solar wind. These charged particles, constantly ejected by the young sun, wreaked havoc across the solar system. Mars, for instance, lacked the protective barrier of a magnetic field, and its atmosphere was mercilessly stripped away, leaving it a barren wasteland, with an atmosphere just 1% as thick as Earth's. Earth was spared this fate, thanks to its molten iron core. The core generated a magnetic field that deflected the solar wind, preserving the fragile layer of gases enveloping the planet. However, this early atmosphere was nothing like the one we breathe today. It was a dense mix dominated by carbon dioxide, a greenhouse gas that traps heat. On Venus, carbon dioxide remains the primary component of the atmosphere, creating a runaway greenhouse effect that has superheated the planet to a hellish 900 degrees Fahrenheit, boiling away its water long ago. So why didn't Earth share Venus's fiery destiny? According to planetary scientist David Crisp, it all came down to a cosmic accident. If Earth had kept all its original atmosphere, it likely would have turned out like Venus, Crisp explains. But that didn't happen. We were the beneficiaries of an incredibly lucky break. This break came in the form of a colossal impact about 4.2 billion years ago. At the time, the solar system was a chaotic swarm of planetesimals, Mars-sized bodies orbiting the Sun in unstable trajectories. One of these, a massive protoplanet, collided with Earth in a violent event that not only blasted away much of Earth's dense, carbon dioxide-heavy atmosphere, but also created the Moon. This monumental collision defined Earth's atmospheric evolution, allowing it to escape Venus's fate. In the aftermath of the impact, Earth's atmosphere was reduced to a mixture of molten and vaporous rock, remnants of the collision. Over millions of years, this material condensed and settled, paving the way for a new atmosphere to emerge. Volcanoes played a crucial role in this transformation, spewing nitrogen, carbon dioxide, and water vapor into the air. Meanwhile, icy comets bombarding the planet delivered additional water, drop by drop, building Earth's first oceans. Despite these changes, the air still lacked one vital ingredient: oxygen. For the first half of Earth's history, the atmosphere contained only greenhouse gases like methane and carbon dioxide. Oxygen, the gas essential for most life today, was conspicuously absent. This changed around 2.5 billion years ago, when cyanobacteria, a humble, microscopic organism, began to flourish. Cyanobacteria are unique in their ability to produce oxygen through photosynthesis, using sunlight to convert carbon dioxide and water into energy, with oxygen as a byproduct. As these microbes spread across the planet's oceans, they released increasing amounts of oxygen into the atmosphere. Dr. Janet Seifert of Rice University highlights the significance of this transformation. Cyanobacteria are the only organisms capable of producing oxygen at the scale necessary to change an atmosphere. Over time, their numbers grew enough to make oxygen a permanent fixture in Earth's air. This pivotal moment, known as the Great Oxidation Event, fundamentally transformed Earth. The buildup of oxygen not only made the atmosphere breathable for future organisms, but also reacted with other gases, stabilizing the climate and enabling the evolution of complex life. What began as a chaotic mix of gases billions of years ago gradually evolved into the life-sustaining atmosphere we know today. This transformation was driven by chance collisions, volcanic eruptions, and the tenacity of tiny microbes, an intricate interplay of forces that turned Earth into a sanctuary for life. Oxygen's rise in the atmosphere was a transformative moment in Earth's history, a force so powerful that it upended the natural order and reshaped life itself. As oxygen began to dominate, everything had to adapt to this new world. The initial impact was felt in the oceans. Oxygen reacted with dissolved iron, creating rust that settled to the seafloor in massive deposits. These deposits became the banded iron formations that now serve as ancient geological records. On land, oxygen's influence turned soil and rock a rusty red as it reacted with surface minerals. Only after these materials had absorbed as much oxygen as they could did the gas begin to accumulate in the atmosphere, setting the stage for dramatic changes. Oxygen's arrival paved the way for the evolution of complex life. With higher oxygen levels, animals could sustain faster metabolisms, unlocking new evolutionary possibilities. Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided. One scientist explains, "This abundance of energy fueled a shift from single-celled organisms to diverse and complex multicellular life. Plants, too, began contributing to oxygen production through photosynthesis, a process they inherited from cyanobacteria. A very ancestral primitive plant cell engulfed a cyanobacterium," explains a biologist, "and instead of digesting it, the cyanobacterium became an organ within the plant. To this day, every molecule of oxygen released by plants traces its origin to cyanobacteria, the ancient pioneers of oxygen production. As oxygen solidified its place in the atmosphere, Earth's unique mix of gases was complete. This air not only sustains life, but also sculpts the planet's terrain and shapes its habitats. However, the atmosphere's contributions extend beyond oxygen. It also plays a critical role in transporting water. As we ascend through the atmosphere, we encounter another vital component: water. The constant motion of air circulates water vapor around the globe, fueling weather systems that shape life on Earth. These movements, driven by the sun's energy, are both destructive and life-giving. Violent storms may flood fields and topple buildings, but without this circulation, the land would be parched and barren. The sun drives atmospheric motion by heating the Earth unevenly. Solar energy warms the equator more than the poles, creating temperature differences that set air in motion. Warm air near the equator expands and rises, while colder, denser air near the poles sinks. This movement creates global air currents that transport heat and moisture across the planet. Marty Ralph, a researcher at NOAA, tracks these patterns using the revolutionary science on a sphere simulator. Here, we can see surface temperatures, Ralph explains. The reds and oranges mark warmer areas near the equator, while blues and greens show cooler polar regions. Watching this, we see warm air moving northward, cold air shifting southward, and the seasonal changes. Without this atmospheric circulation, the planet's climate would be radically different. The poles would be 45 degrees Fahrenheit colder, locked in eternal ice, while the equator would be 25 degrees Fahrenheit hotter, scorched by relentless heat. Vast deserts like the Sahara and Mojave would expand unchecked. And northern cities like London and Boston would face permanent winters. It is the movement of the atmosphere that redistributes heat and prevents these extremes, creating the temperate, livable conditions we experience today. The atmosphere's circulation also drives dramatic weather events. As air moves across the rotating Earth, it twists into hurricanes that batter coastlines with fierce winds and rain. Rising moist air generates towering clouds that discharge lightning bolts, superheating the air to a staggering 18,000 degrees Fahrenheit. Rain falls as the air cools, replenishing the land with water carried from the world's oceans. At any moment, a tiny fraction, just 0.001%, of Earth's water is suspended in the atmosphere as vapor. This may seem insignificant, but it amounts to nearly 3,000 cubic miles of liquid. Without this vapor cycling through the atmosphere, the land would dry out entirely, and life as we know it would cease. Through its ability to transport water, regulate temperature, and sustain life, the atmosphere remains one of Earth's most remarkable systems. It is an ever-moving force that shapes the weather, nourishes ecosystems, and makes our planet a haven in the vastness of space. Storms play a crucial role in Earth's atmospheric balance. By reducing the temperature differences between the poles and the equator, they redistribute heat, creating the rain and snow essential for ecosystems and human life. Among the most remarkable weather phenomena are newly discovered atmospheric rivers, massive channels of water vapor that flow through the skies. Atmospheric rivers, as described by researcher Marty Ralph, are narrow bands of hurricane-force winds that can stretch thousands of miles. These rivers in the sky carry immense quantities of water vapor, up to 3 times the volume of the Mississippi River. They deliver nearly half the annual rainfall to parts of the American Pacific coast, replenishing vital water supplies. However, when they linger over an area for extended periods, the result can be catastrophic flooding. Heavy winds, lots of water vapor, and a storm track that isn't moving fast. It all adds up to a big flood, Ralph explains. Despite their significance, atmospheric rivers remain challenging to predict. They form over vast oceans where weather data is sparse. For instance, a forecast might predict heavy rain in Northern California, but the same river could shift northward and deliver that rain to Canada instead. A dramatic difference that underscores the need for better data. To close this knowledge gap, Ralph and his team conduct research flights directly into these rivers. Using specialized equipment, they measure temperature, wind speeds, and humidity within these high-speed conveyor belts of water vapor. These rivers often form ahead of cold air masses, and transport moisture from the oceans to the coasts at speeds of up to 100 miles per hour. When the water-laden air encounters mountains, it rises, cooling and shedding its moisture as rain or snow. These rivers are narrow but incredibly powerful, Ralph notes. They account for 90% of the water vapor transport in the global atmosphere at mid-latitudes. His research has tracked seasonal patterns in the river's movements, but accurately forecasting floods will require more comprehensive data. Ralph envisions fleets of robotic drones continuously monitoring atmospheric conditions over the oceans, measuring changes in wind, temperature, and water vapor to improve predictions. There's growing evidence that climate change may be intensifying atmospheric rivers. We're starting to see that the more intense rivers are becoming more frequent in certain parts of the world, Ralph explains, and this will contribute to increased flooding. These changes are part of a broader transformation in Earth's climate and atmosphere, driven by human activity. Deserts are expanding, rainforests are drying out, and weather patterns are becoming increasingly erratic, all due to shifts in the chemical makeup of the atmosphere. While natural fluctuations in atmospheric gases have occurred throughout Earth's history, human activity has dramatically accelerated these changes. Factories, homes, vehicles, and planes release vast quantities of greenhouse gases, particularly carbon dioxide, CO2, into the air. Over the past 2 centuries, atmospheric CO2 levels have risen to unprecedented heights, amplifying the greenhouse effect. For now, Earth's natural systems have absorbed much of this excess carbon dioxide. Oceans, especially the North Atlantic, have acted as enormous carbon sinks, pulling nearly 55% of CO2 emissions out of the atmosphere. But these safety valves are nearing their limits. The North Atlantic has absorbed a tremendous amount of carbon dioxide, Ralph notes, but it's almost completely saturated. It's like a bottle of soda. If you warm it up even slightly, it will fizz and release CO2 back into the air. As oceans reach their saturation points, their ability to buffer climate change diminishes, leaving the atmosphere to bear the brunt of rising CO2 levels. If CO2 emissions continue unabated, Earth will face a dramatic rise in global temperatures. Projections suggest the planet's average temperature could increase by as much as 7 degrees Fahrenheit by the end of the century. Such a rise would have far-reaching consequences. Melting polar ice caps, rising sea levels, intensified storms, and shifting weather patterns that could destabilize ecosystems and human societies alike. The atmosphere, once a delicate balance of gases that nurtured life, is now in flux, strained by human activity. Atmospheric rivers, once vital for delivering water, may turn into harbingers of destruction, while natural carbon sinks fail to keep pace with the growing emissions. To secure a livable future, humanity must act swiftly to curb emissions and protect the fragile balance of our atmosphere. Earth's atmosphere has evolved over billions of years to become the life-supporting system we rely on today. Now, its fate, and ours, rests on our willingness to adapt and mitigate the impacts of our own actions. The atmosphere, with its unique blend of gases, is vital to life on Earth. Its delicate balance sets our planet apart from others in the solar system, shielding us from radiation and stabilizing our climate. Yet, as we ascend beyond the turbulent clouds and winds of the troposphere, we enter an alien world, a realm of extreme temperatures and thinning air that, while deadly to humans, is essential for protecting life below. We live within a thin layer of the atmosphere called the troposphere, which extends roughly 40,000 feet above Earth's surface. This is where weather happens, Winds, rain, snow, and storms dominate. Above the troposphere lie layers of cold, dry air that seem inhospitable but are critical to shielding Earth from cosmic radiation and solar winds. Despite its dangers, the upper atmosphere remains a frontier of exploration, where scientists like John Powell and his team of balloon engineers venture to uncover its mysteries. Powell's team has spent nearly 3 decades probing the atmosphere's higher reaches, conducting over 90 launches to explore this vast alien environment. Sometimes we run into phenomena we can't explain, Powell says. It's like entering a foreign world. Their ultimate goal is ambitious: to reach space using balloons or airships, offering an alternative to rocket-based space travel. Officially, space begins at 62 miles above Earth's surface, marking the boundary where the atmosphere thins into the vacuum of space. On a tabletop globe, this would appear as thin as a coat of varnish. Yet, in reality, Earth's atmosphere stretches much farther, gradually fading into the exosphere. Earth's atmosphere is divided into distinct layers, each defined by changes in temperature. Beyond the troposphere lies the stratosphere, a calm, stable zone where temperatures increase slightly due to the absorption of solar radiation by the ozone layer. This stability makes it an ideal region for high-altitude balloons and long-duration flights. Above the stratosphere, the mesosphere plunges to frigid temperatures of -50 degrees Fahrenheit, making it the coldest part of the atmosphere. Yet, this layer plays a critical role in burning up meteoroids, protecting Earth from countless cosmic impacts. Beyond this lies the thermosphere, where solar radiation causes temperatures to soar as high as 4,500 degrees Fahrenheit. Despite this extreme heat, the air is so thin that it would feel cold to a human, because there are too few particles to conduct heat effectively. Finally, at the edge of the atmosphere lies the exosphere, a nearly infinite expanse where air molecules are so sparse they rarely collide. The exosphere is incredibly high, Powell notes. During the Apollo program, particles from Earth's atmosphere were detected on the far side of the Moon. As Powell's balloons rise through these layers, they leave the familiar conditions of Earth behind. The air grows thinner, and the protective weight of miles of atmosphere diminishes. At the stratosphere, the pressure is only 1/100th of what it is on the ground, Powell explains. It's a completely different world. We often think of air as weightless, but it is anything but. The atmosphere presses down on everything at sea level, exerting a force we call air pressure. In New York's Grand Central Station, the main concourse contains over 200 tons of air. Gravity compresses the atmosphere, making the air denser closer to the ground. This dense air is what we experience every day, with a single pint containing over 8.5 billion trillion gas molecules. As Powell's balloons ascend, the layers of air thin. Imagine the atmosphere as a stack of blankets, each layer pressing down on the one below. As you go higher, Powell says, you're moving through the blankets, so the pressure lessens until you reach the top, where you barely feel it at all. This thin, alien air may seem hostile, but it is critical to life on Earth. It carries sound waves, pulsing pressure changes that allow us to hear. Sound is like a ripple in water, Powell explains. It travels through the air as waves of pressure. Without dense air to carry these waves, sound would not reach our ears. Despite its challenges, the high atmosphere offers immense scientific opportunities. Powell and his team push the limits of exploration, seeking new ways to utilize this remote region. Their work highlights the atmosphere's fragility and importance. It's a layered cocoon. sheltering Earth and nurturing life, while simultaneously acting as a gateway to the vastness of space. As humanity continues to study and explore these layers, we gain a deeper appreciation for their role in regulating our climate, sustaining life, and opening the door to space exploration. The atmosphere is not just a shield, it's a dynamic, living system, our planet's first and greatest line of defense. The atmosphere, though fragile, is Earth's steadfast protector against the harshness of space. Yet, as we ascend higher, its ability to carry sound, sustain life, and shield us weakens until it fades into the vacuum of space, a realm of silence where even the largest explosions go unheard. This concept is vividly demonstrated through simple school science experiments aboard John Powell's high-altitude balloons. We call it a PATI for ping-pong ball satellite, Powell says, describing the process. You cut a ping-pong ball in half, place a small object inside, like a marshmallow, and send it to the edge of space. In the stratosphere's thin air, the marshmallow, once held together by high pressure, swells and bursts as the air bubbles within it expand. This phenomenon isn't just a fun experiment. It underscores the dangers of thin air for living organisms. Contrary to popular belief, a lack of pressure wouldn't cause human blood to boil, as blood vessels hold it in place. However, exposed flesh would swell painfully, much like the marshmallow. Above 26,000 feet, the air is too thin to sustain life. Each lungful contains so few oxygen molecules that the brain begins to shut down. The extreme cold would kill you, Powell notes, but the lack of pressure would get you first. As Powell's balloons ascend higher, they face another deadly challenge: solar radiation. Every day, the sun bathes Earth in a deluge of energy, including high-energy ultraviolet UV rays. In the upper atmosphere, these rays attack the structure of Powell's balloons, causing microscopic cracks that weaken the material until it fails. The UV literally damages the material, Powell explains. Eventually, the balloon pops. But UV rays are far more dangerous to humans than to balloons. They bombard cells and DNA, increasing the risk of cancers. Thankfully, a layer of the atmosphere about 7 miles above Earth, the ozone layer, blocks 99% of these rays. Composed of ozone molecules, 3 oxygen atoms bonded together, this layer absorbs and dissipates UV radiation. The ozone layer isn't like a saran wrap boundary, Powell explains. It's miles thick, gradually thinning out as you ascend. However, this crucial shield has been under threat from man-made chemicals like chlorofluorocarbons, CFCs, once widely used in refrigerators and aerosols. These chemicals caused significant damage to the ozone layer, leading to seasonal holes over the poles. Thanks to global bans on CFCs, the ozone layer is now recovering, slowly regaining its strength. Above the ozone layer lies the mesosphere, where the atmosphere continues its protective work. Here, it shields Earth from another peril: meteorites. Every year, over 18,000 meteoroids hurtle toward Earth at thousands of miles per hour. Most of these space rocks burn up in the mesosphere, their fiery demise creating the shooting stars we see in the night sky. Meteorite hunters like Jeff Notkin and Steve Arnold, however, seek out the rare fragments that survive this fiery entry. The atmosphere is our friend because it protects us, Notkin says. But for meteorite hunters, it's also a challenge because it burns up a lot of what we're looking for. Using custom-built metal detectors, they search for meteorites which are often rich in iron and respond to magnets. Their quest has taken them across the globe, from Siberia to Chile, with remarkable finds along the way. Steve Arnold recalls his most extraordinary discovery, a 1,430-pound stony iron meteorite unearthed in Kansas. "We didn't realize it was such a big deal," he says modestly, though the find became one of the most significant in meteorite history, valued at nearly $1 million. But such discoveries are rare. The vast majority of meteoroids disintegrate before reaching the surface, their material scattered as dust across the planet. For meteorite hunters, each surviving fragment is a precious relic, a tangible piece of the cosmos that offers insight into the formation of our solar system. As meteoroids collide with Earth's atmosphere, they carry the momentum of their interstellar journey, often traveling at tens of thousands of miles per hour. The atmosphere acts as a brake, compressing and heating the meteoroids until most disintegrate. This protective barrier is why Earth has been spared catastrophic impacts from space rocks that could otherwise devastate life. The atmosphere's layers, each with its distinct characteristics, work in concert to safeguard life on Earth. From blocking harmful UV radiation to vaporizing meteoroids, they provide a shield against external threats. Yet, as Powell's balloon experiments remind us, the atmosphere is also a fragile system. Its delicate balance of gases, pressure, and temperature is critical not only for protection, but for sustaining the ecosystems and climates we rely on. The journey through the atmosphere reveals a world of contrasts, a realm that nurtures life at its base while battling cosmic forces in its upper reaches. It is a dynamic, ever-changing system, a testament to Earth's unique ability to support life in the vast emptiness of space. As we continue to explore and understand its layers, we gain a deeper appreciation for the vital role it plays in making our planet habitable. As meteorites cut through the outer reaches of Earth's atmosphere and descend into the mesosphere, they encounter a force they cannot escape: air resistance. Though invisible to us, the air becomes a formidable barrier to objects traveling at incredible speeds. When a meteorite encounters our atmosphere, explains one expert, it's moving so quickly that the air in front of it can't get out of the way. It's as if the meteorite is hitting a solid wall of concrete. This resistance compresses the air in front of the meteorite, generating intense heat, reaching temperatures of over 30,000 degrees Fahrenheit. The fiery compression creates the brilliant streak of light we see as a shooting star. But what burns isn't the meteorite itself. It's the protective air around it that ignites, acting as Earth's shield. However, the intense heat and friction do take a toll on the meteorite. The scorching air melts its outer layers, while the sheer force of its passage through the atmosphere can exploit any natural fissures, shattering it into smaller fragments. If this meteorite were to encounter the atmosphere at high speed in its current condition, an expert demonstrates, it would break apart completely. What survives the fall to Earth are mere remnants of the original asteroid, reduced from massive boulders traveling at 177,000 miles per hour to fragments the size of golf balls hurtling at a mere 300 miles per hour. The search for these fragments is a painstaking task. Meteorite hunters comb the ground with specialized metal detectors, but the odds are stacked against them. For every genuine find, they uncover dozens of meteor wrongs, ferrous objects mistaken for meteorites. We uncover about 75 meteor wrongs for every meteorite we find, says one hunter. The genuine articles are unmistakable, distinguished by unique features like regmaglypts, indentations caused by the melting surface during the meteorite's fiery descent. These thumbprint-like markings are exclusive to meteorites, the hunter explains, and you won't find them on Earth rocks. Meteorites hold a rare and fascinating allure, as they are fragments of ancient celestial bodies, pieces of asteroids or planetary cores that have traveled billions of miles through space. Their survival depends entirely on the protective qualities of Earth's atmosphere. Without it, the planet would be bombarded by countless space rocks every day, many of them large enough to cause significant damage. Our atmosphere is the reason these impacts are rare, one scientist remarks. Without it, we'd have particles raining down constantly, and some of them wouldn't be so small. The mesosphere, with its thin barrier of air, is one of the final defenses against these cosmic intruders. It adds to the many gifts of our atmosphere: the oxygen we breathe, the water we drink, and the pressure that supports life. Yet, as we ascend beyond this layer, the environment becomes increasingly hostile. Above the mesosphere lies a realm where air is sparse and life is unsustainable. Explorers like John Powell, whose airships have reached the upper stratosphere, and Joseph Kittinger, who jumped from the middle of the stratosphere, push the limits of human exploration. But even they have yet to breach the truly alien realms above, where Earth's atmosphere fades into the vacuum of space. The thermosphere and exosphere are the realms of Earth's atmosphere that only astronauts pass through, a superheated transition to the vacuum of space. These distant layers may one day be the starting point for humanity's journeys to other planets, each with its own alien atmosphere, atmospheres that could potentially harbor life. Astronomer Joel Hagen has spent 2 decades envisioning how extraterrestrial atmospheres might shape the lives of their inhabitants. The creative joy, Hagen says, comes from imagining everything we know here on Earth, and then taking it one step further, visualizing what we haven't seen yet. One scenario Hagen considers is life thriving in the dense gaseous layers of a gas giant like Jupiter. Such a world, with no solid surface and a gradual transition of gas densities, presents an entirely alien environment. Hagen speculates that creatures in such an atmosphere might rely on buoyancy to stay aloft. I imagine organisms that generate hydrogen within their bodies, Hagen says, like hydrogen-filled blimps, allowing them to float among the gas clouds. He envisions these life forms as having balloon-like structures inflated with hydrogen, with colonies of microbes residing within tentacle-like appendages. These microbes could produce hydrogen to sustain their host, enabling it to drift freely at optimal levels in the dense atmosphere. On planets with denser atmospheres and lower gravity than Earth, Hagen imagines even larger, more complex creatures taking to the skies. A thicker atmosphere could support bulkier bodies, allowing flight to become a viable evolutionary strategy for large organisms. On a planet like Titan, where surface gravity is only 15% of Earth's, but atmospheric density is 1.5 times greater, Hagen explains, even a human with wings could take flight. In such environments, massive gliding reptiles or other winged creatures might dominate the skies. Hagen bases these speculations on known planetary conditions and the evolutionary principles observed on Earth. But he acknowledges the speculative nature of his work. I'd be thrilled just to find microbes under rocks on Mars, he admits. Life doesn't need to walk up and shake hands with me. Just knowing it has happened twice would be enough. For now, humanity remains alone in the universe. Life, as far as we know, has occurred only once, and only because of Earth's singular atmosphere. This remarkable mix of gases, forged over billions of years, has shielded and nurtured our planet, creating an environment uniquely suited for sustaining life. As we've traveled through the atmosphere, rising from the ground to the edge of space, we've explored this life-sustaining ocean of air. It shields us from radiation, burns up meteoroids, provides the oxygen we breathe, and supports the water cycle that sustains ecosystems. Our atmosphere is not just a blanket of gases. It's a dynamic and delicate system, the cornerstone of life on Earth. And as humanity continues to look outward, seeking life in alien worlds, we are reminded of how rare and precious our own atmosphere truly is. A fragile gift that makes life possible in the vast emptiness of space. As we've explored Earth's atmosphere, we've seen how it shields, sustains, and shapes life on our planet. But this delicate balance hasn't always been stable. In its distant past, Earth faced extreme transformations that pushed its atmosphere and climate to their limits. One of the most dramatic episodes in our planet's history was a time when Earth turned into a frozen sphere, a snowball Earth. How did this happen? And how did life manage to survive such a hostile environment? Let's journey back to uncover the icy secrets of this remarkable chapter in Earth's story. Life as we know it exists because of a series of extraordinary and often catastrophic events. 99% of all species that have ever lived on Earth are now extinct, wiped out by disasters that reshaped the course of evolution. One of the most dramatic of these events occurred 650 million years ago, when the entire planet froze. A phenomenon now known as Snowball Earth. This ancient disaster pushed life to the brink of extinction. Yet, paradoxically, it also paved the way for the incredible diversity of life that we see today. Without this icy apocalypse, complex organisms, including humans, might never have evolved. The story of Snowball Earth is one of survival against all odds, and it marks a turning point in Earth's history. To grasp the immense timeline of our planet, imagine compressing Earth's 4.5 billion-year history into a single day. At midnight, the planet forms. Minutes later, a collision with the protoplanet Theia gives birth to the Moon. By 4 a.m., primitive life appears, and by 8 a.m., shallow seas are teeming with bacteria. These simple organisms dominate for billions of years, colonizing the oceans and steadily shaping the planet's environment. Then, at 8:27 p.m., 650 million years ago, disaster strikes. Temperatures plummet, and ice spreads relentlessly from the poles toward the equator. The entire planet becomes encased in ice, turning into a frozen sphere, a snowball Earth. Life, still in its infancy, is nearly wiped out. Earth remains locked in this icy state for 25 million years before it finally thaws. Remarkably, some microorganisms survive, and when the ice retreats, they trigger one of the greatest leaps forward in evolution. The very catastrophe that seemed destined to extinguish life instead catalyzed the emergence of complex organisms, setting the stage for the rich biodiversity of today. How do scientists know that this extraordinary event occurred? The ancient ice sheets themselves have long since disappeared, but the evidence of Snowball Earth is written in the rocks of some of the most remote and inhospitable places on the planet. One such location is the Flinders Ranges in the Australian outback. This scorching, arid landscape is now one of the hottest places on Earth, making it hard to imagine it was once a frozen wasteland. Yet, for geologist Jim Geiling, this harsh environment holds critical clues to Earth's coldest period. Investigating the vast expanse of the Flinders Ranges often requires aerial surveys, but the most telling evidence is found on the ground, embedded within the layers of ancient rock. There's a disaster story written in these layers of rock, Geiling explains. It's like reading a history book. Every layer holds a secret. In a dried-up creek bed, Geiling discovers a key piece of evidence, a 650 million-year-old dropstone. At first glance, the rock appears unremarkable, but its location is baffling. It sits embedded in fine mud, silt, and sand, a geological impossibility under normal conditions. A dropstone is a piece of rock transported thousands of miles from its place of origin. The only force capable of carrying such a rock across vast distances and depositing it amidst fine sediment is ice. During Snowball Earth, glaciers carried massive rocks embedded within the ice. As the icebergs drifted into the oceans and began to melt, these rocks were released, falling into the soft seabed below. Over millions of years, layers of mud and sand buried the dropstones, preserving them as evidence of this global freeze. This rock shouldn't be here, Geiling emphasizes. It's a clue to the immense power of ice and the dramatic forces that shaped Snowball Earth. The presence of dropstones in places like the Flinders Ranges is a testament to the planet's frozen past. These scattered relics reveal a world where glaciers extended to the tropics, where life was forced to adapt or perish in one of the most extreme environments Earth has ever known. The Snowball Earth episode was both a disaster and a turning point. It tested life to its limits, wiping out countless species while driving the survivors to evolve in ways that would forever alter the trajectory of life on Earth. Through ancient rocks and the secrets they hold, we can piece together the story of this frozen chapter in Earth's history, a story of resilience, transformation, and the enduring power of life. To understand how glaciers could have moved massive rocks across the globe during the Snowball Earth period, scientists like glaciologist Shad O'Neill turn to modern ice sheets, such as Alaska's Matanuska Glacier. While much smaller than the ancient glaciers of 650 million years ago, the Matanuska Glacier operates in the same way, providing a window into Earth's frozen past. Glaciers are nature's bulldozers, O'Neill explains. They smash through everything in their path, gouging stones and rocks from mountains and transporting them across vast distances. Rocks as large as buses can be carried for miles by glaciers, and the largest ice sheets of ancient Earth spanned thousands of kilometers. These glaciers had the power to deposit rocks far from their points of origin, a process that left behind clues like the dropstones found in Australia's Flinders Ranges. But, as dramatic as these events are, such localized eruptions wouldn't have made much difference during Snowball Earth. The planet's frozen grip required more than just a few holes in the ice. It demanded a global-scale intervention. Volcanoes have another, more far-reaching weapon: greenhouse gases. Eruptions release vast amounts of gases like carbon dioxide, CO2, into the atmosphere. Power estimates that Mount Augustin alone has ejected thousands of tons of CO2 per day during its most active periods. On Snowball Earth, the sheer number of active volcanoes was staggering. Scientists believe that thousands of eruptions across the globe pumped billions of tons of CO2 into the atmosphere over millions of years. This gradual buildup of greenhouse gases reversed the conditions that had triggered the global freeze. Carbon dioxide levels rapidly increased until they reached a critical point, Power explains. This led to a super meltdown of the ice, effectively the death knell of Snowball Earth. As CO2 accumulated, it trapped sunlight and warmed the planet. The runaway freezing effect that had turned Earth into a snowball was finally halted, and the ice began to retreat. Slowly but surely, temperatures rose, and the planet emerged from its icy prison. As the ice sheets melted, a new chapter in Earth's history began. The end of Snowball Earth coincided with one of the most significant evolutionary leaps the planet has ever seen. For billions of years, life had been dominated by simple, single-celled organisms. But the post-freeze environment created opportunities for life to diversify and grow. Nutrients from the melting ice flooded the oceans, fueling an explosion of complex life forms. This leap in evolution set the stage for the development of multicellular organisms, eventually leading to the rich biodiversity we see today, and to us. 635 million years ago, the same forces that had caused devastating eruptions became the planet's saviors. By releasing billions of tons of CO2, volcanoes tipped the balance, reversing the Ice Age and setting Earth on a trajectory toward warmth and life. The story of Snowball Earth is a testament to the dynamic interplay of Earth's systems. From volcanic heat to icy resilience, these processes have shaped our planet in ways that continue to impact us. As Power reflects, volcanoes didn't just thaw the Earth, they set the stage for the evolution of life as we know it. The scars of Snowball Earth may be long gone, but the lessons remain. Even in the planet's darkest, coldest times, forces from within can drive renewal, change, and life itself. The end of Snowball Earth marked not just the thawing of a frozen planet, but the beginning of a profound transformation in the history of life. After a 25 million year freeze, the buildup of carbon dioxide in the atmosphere finally trapped enough heat from the sun to melt the ice. The planet emerged from its icy prison, and life, against all odds, was ready to seize its moment. Beneath the ice, single-celled organisms had clung to existence in the dark, cold oceans. But with the ice gone and the climate warming rapidly, these simple life forms underwent an extraordinary evolution. Just 3 million years after the deep freeze ended, the world witnessed an evolutionary explosion. Single-celled bacteria gave rise to multi-celled organisms, the first complex life forms. These early creatures became the ancestors of every living animal, including humans. Today, every living thing on Earth owes its existence to this frozen chapter in the planet's history. From the simplest microorganisms to the most complex animals, all life traces its lineage back to the survivors of Snowball Earth. Snowball Earth was the greatest climate disaster the planet has ever known, but it was also its greatest turning point. Without the Ice Age, the evolutionary leap that led to complex life forms, and eventually to humans, might never have occurred. From a world of slime to a planet teeming with life, Snowball Earth transformed Earth forever. It turned catastrophe into creation and shaped the course of evolution in ways that still resonate today. As we reflect on our origins, one thing becomes clear. We owe our existence to the extraordinary resilience of life and to the transformative power of Earth's greatest freeze. Snowball Earth was a defining moment in the planet's history. A catastrophic freeze that nearly wiped out life, only to ignite an evolutionary leap that led to the complex creatures we see today, including ourselves. But as life adapted and evolved through Earth's ever-changing conditions, it faced challenges that would have made human survival impossible. This begs the question, if we could travel back in time, how far into Earth's history could we have survived? Let's journey through the ages to find out. The capsule shudders as the temporal engines slow, jolting the traveler from their anxious thoughts. The whirring hum of the time machine reaches a crescendo before abruptly cutting out, leaving only the sound of the traveler's own breathing in the recycled air of the pod. The digital readout on the screen flashes 4,500,000,000 years ago. They have arrived at the very beginning of Earth's history, a world so alien that it hardly resembles the home they know. Tentatively, the traveler peers through the curved glass windows, half expecting to see a familiar, albeit primitive, version of Earth. Instead, they are greeted by a vast, searing void. The sun, a younger, hotter version of the star they had just left behind, blazes fiercely in a black sky, unsoftened by any atmosphere. The Earth below, or what passes for it, is a violent and chaotic landscape, a molten inferno of bubbling lava and roiling clouds of toxic gases. This is no planet for life. It is barely a planet at all. A newborn world still in the throes of formation. The time traveler's heart pounds as they take in the apocalyptic scene. Vast rivers of molten rock snake across the surface, flowing into glowing orange lakes of magma. In the distance, massive volcanic eruptions puncture the airless sky, spewing ash and gas with an intensity that shakes the ground even from within the capsule. There are no continents, no oceans, no signs of stability. The air outside is a poisonous cocktail of carbon dioxide, sulfur dioxide, and methane. While temperatures are so high that even the thought of stepping outside is unthinkable. The traveler now understands why they were warned this early world might be inhospitable. Not even the most advanced protective suits could shield them here. For a paleontologist accustomed to piecing together fragments of the past, this living, breathing chaos is overwhelming. The time traveler had long studied the ancient rocks of Earth, imagining the world that must have existed when they were formed. Yet nothing could have prepared them for the raw power and sheer hostility of this primordial landscape. Suddenly, a flash streaks across the blackness. A massive asteroid blazing through the sky before slamming into the molten ground with a force that shakes the pod violently. The traveler grips the console, realizing they are witnessing one of the countless impacts that helped shape Earth in its earliest days. These collisions, they know, brought not only destruction, but also the seeds of creation, delivering the essential building blocks of water, minerals, and organic molecules that would one day give rise to life. But in this moment, the scale of destruction is staggering. The impact sends a plume of molten rock and dust shooting into the void, raining fire and ash down on the surrounding landscape. The traveler marvels at the resilience of the planet itself, slowly transforming under such relentless bombardment. Despite the hellish environment, the traveler can't help but feel a sense of awe. They know that this molten wasteland is the beginning of the Earth's long journey to becoming a cradle for life. Over the next billions of years, this fiery chaos will cool and stabilize. Oceans will form, the atmosphere will develop, and continents will rise. What seems like an uninhabitable inferno now is the foundation of a world that will one day teem with life. As the traveler studies the screen, contemplating their next move, they can't help but wonder, when will the Earth finally become a place where humans, or any kind of life, could survive? Could they bear witness to the first drops of liquid water pooling on the surface? To the creation of the earliest land masses? Or would even those times still prove too hostile? The traveler realizes that while they are safe within the capsule, they cannot stay here. The Earth of 4.5 billion years ago is magnificent, but entirely uninhabitable. It is time to move forward, to search for a more hospitable era, an Earth with water, an atmosphere, perhaps even the first stirrings of life. Adjusting the dials, they input a new date, millions of years ahead, and prepare for the next leap through time. As the engines power up again, the molten world outside begins to blur and distort, receding into a fiery haze. The traveler steadies their nerves, ready to face whatever comes next. This journey, after all, is about more than survival. It is about understanding how a barren, lifeless rock became the only home humanity has ever known. As the time traveler steadies themselves in the capsule, they are struck by the harshness of the scene outside. The Hadian Earth, still young and volatile, is a far cry from the blue and green world they know. The land beyond the capsule's curved glass windows is scorched and barren, a landscape of molten rock and jagged ridges glowing faintly orange against the dim, surreal light of the sun. Rivers of lava flow unceasingly, carving chaotic paths through a crust that is still thin and fractured. Volcanoes erupt with violent regularity, spewing plumes of ash and gas into a sky tinged faintly blue, but suffused with a fiery orange hue from the surface below. The traveler's instruments provide a grim reminder of the planet's hostility. Alarms shriek warnings of extreme heat, unstable terrain, and seismic activity. The capsule shakes slightly as distant impacts reverberate through the planet, likely from massive asteroids that still rain down on this unformed world, leaving fresh scars on its surface. Looking up, the traveler notes that the sky itself is unlike anything they've ever seen. The atmosphere is thin and alien, composed mostly of hydrogen and helium, with traces of methane and ammonia. It fails to scatter sunlight effectively, leaving the heavens dim even at midday. At night, this faint atmosphere would provide no protection from the stars' unfiltered light, or the harsh cosmic radiation that bathes the planet. Despite its fragility, the thin veil of gases swirls chaotically, pushed by the relentless heat rising from below. It carries with it noxious compounds that escape from the molten surface: carbon dioxide, sulfur dioxide, and even traces of hydrogen sulfide, creating a toxic cocktail that would render even the smallest breath lethal. The ground shakes once again, this time with more force, and a flash of light streaks across the sky. Another asteroid, glowing white-hot as it plummets through the thin atmosphere, slams into the planet with catastrophic force. The impact sends shockwaves rippling across the terrain, and a plume of molten debris rises into the sky before settling back into the fiery landscape. This is not an unusual event. The Hadian Earth is in the throes of the late heavy bombardment, a period when asteroids and comets relentlessly pummel the planet, delivering not only devastation, but also the raw materials, water, and organic molecules that will one day make life possible. Despite its hostility, there is an undeniable beauty to this chaos. The traveler gazes at the molten rivers, the glowing craters, and the volcanic plumes, marveling at the raw energy and transformative power at work. This is the crucible of creation, a planet forging itself from the ashes of stellar debris, preparing for the eons of change to come. For now, though, survival here is impossible. The traveler's instruments confirm what they already know. This is not a place for humans. Even within the capsule, insulated from the searing heat and poisonous gases, the traveler feels the weight of the environment pressing against the fragile seals that keep them alive. The traveler takes a deep breath of the cool, recycled air inside the pod and adjusts the controls for their next leap forward in time. This is only the beginning of Earth's story. For billions of years, this molten hellscape will cool and solidify, forming the crust that will one day host oceans, continents, and life. But for now, the planet is still young and wild, a place of relentless destruction and creation. With a flick of a switch, the engines power up once more, and the capsule begins to ascend through the violent haze of the Hadian Earth, carrying the traveler forward to the next chapter of the planet's history. As the time machine stabilizes in its new temporal position, the traveler takes a long, calming breath. The tumultuous chaos of the Hadian has been replaced by an entirely different landscape. Through the capsule's curved glass, they gaze out at a scene that is almost tranquil by comparison. A vast expanse of deep blue ocean stretches to the horizon, broken only by the occasional ripple of waves. The transition is startling. This is Earth, but it is now the Archean Earth. Some billion years after the fiery trials of planetary formation, and its transformation is breathtaking. The once barren and molten surface has cooled and hardened, giving way to a world dominated by water. There are no continents as we know them, only small, jagged proto-islands of volcanic rock peeking above the waves. The traveler's capsule bobs gently on the surface, its sensors providing vital data about the conditions of this nascent oceanic world. The temperature outside is strikingly warm, registering around 30 degrees Celsius, akin to the tropical climates the traveler left behind in the 21st century. It is a surprising revelation. With the young sun still dim and only 3/4 as luminous as it will eventually become, Earth's surface should be locked in ice. Yet the oceans are liquid, and the air is warm, a paradox that demands an explanation. The answer lies in the hazy, orange-tinged sky above. The atmosphere is dense and heavy, rich in greenhouse gases that trap the sun's heat with remarkable efficiency. Carbon dioxide and methane dominate this primitive atmosphere, creating a powerful insulating effect. Methane, released from the volcanic activity that still churns beneath the surface, plays a particularly crucial role. It is a potent greenhouse gas, far more effective than carbon dioxide at retaining heat, and its abundance compensates for the sun's relative dimness. The traveler, now cautious after their brush with disaster in the Hadian, uses the capsule's instruments to analyze the air and water without stepping outside. The results are fascinating. The oceans, vast and uninterrupted, are slightly acidic, with a pH akin to orange juice. This mild acidity stems from the carbon dioxide dissolving into the water, forming carbonic acid. While harmless to the traveler, this chemical composition will play a critical role in shaping Earth's future, influencing the formation of minerals and the eventual emergence of life. The sky itself is a blend of familiarity and alienness. While it bears the same hazy blue hue of modern Earth, the orange and gray overtones hint at its primitive makeup. Clouds of water vapor form towering structures, swirling and breaking apart in patterns dictated by the atmosphere's density and the planet's rapid rotation. There is no oxygen yet, no breathable air for the traveler. But nitrogen and other gases, alongside the greenhouse components, create a unique and evolving environment. Occasionally, faint glimmers streak across the sky. These are not meteors from the late heavy bombardment, but rather the remnants of smaller debris still finding their place in the young solar system. Unlike the relentless impacts of the Hadian, these occasional visitors are a sign of a planet settling into relative stability. While there are no fish, plants, or reefs to decorate these early oceans, they are far from barren. Beneath the capsule, the traveler's instruments detect the faint chemical traces of primitive life. Microbial mats of cyanobacteria clinging to the rocky substrates of the proto-islands. These simple organisms are among the first living things on Earth, quietly transforming the planet with their metabolic processes. By converting sunlight and carbon dioxide into energy, they produce oxygen as a byproduct, laying the groundwork for an atmosphere that will one day support complex life. The traveler marvels at this subtle but profound activity. The cyanobacteria are microscopic pioneers, shaping the world in ways that will only be understood billions of years later. The faint greenish tint on some of the volcanic rocks hints at their presence, a sign of life's tenacity and potential. The traveler reflects on the incredible transformation that has occurred in just 1 billion years. From a molten, inhospitable hellscape, Earth has become a world of water and burgeoning life. It is still far from being a home for humans, but the potential is unmistakable. The oceans are a cradle, nurturing the first steps of biological evolution. With a renewed sense of curiosity, the traveler adjusts the capsule's controls. This is only the beginning. Ahead lies the slow march of continental drift, the rise of oxygen, and the eventual explosion of complex life. The traveler can't help but wonder, how far forward must they go before the Earth becomes a place they could call home? With a flick of a switch, the capsule begins its next leap forward in time, leaving the Archean Earth and its primordial beauty behind. As the traveler peers out from their capsule, the Archean Earth reveals itself as a world of contrasts, both hauntingly alien and eerily familiar. Towering clouds cycle water vapor endlessly between the ocean's surface and the sky, their colossal forms scattering the sunlight into a soft, diffused blue. Yet the familiar daytime sky hides a lethal secret. The very air that cloaks the planet is devoid of life-sustaining oxygen. What fills the atmosphere instead is a mix of nitrogen, carbon dioxide, and methane, creating a world hostile to the traveler's existence. The traveler studies the readings from the onboard instruments. Nitrogen, as it does today, makes up the majority of the atmosphere, but the absence of oxygen is stark. Carbon-bearing molecules, particularly carbon dioxide and methane, occupy up to 15% of the air. These gases, though invisible, define the Archean world in profound ways. Carbon dioxide dissolves into the oceans, forming carbonic acid that gives the water its slight acidity. This process accelerates the chemical weathering of the ocean floor, where grains of sand and mud eroded from submerged volcanic ridges settle. The traveler notes that the ocean, though warm and inviting in appearance, is a place of constant transformation, a crucible where geology and chemistry intertwine. Meanwhile, the upper atmosphere is shrouded in a faint orange haze, the result of sunlight reacting with methane and carbon dioxide. These reactions create complex organic molecules, scattering light and tinting the sky. Though thinner and more diffuse than Titan's thick haze, it still dims the sunlight, and gives the world an otherworldly glow. The paradox of the warm tropical climate, despite the faint young sun, puzzles the traveler no longer. Methane and carbon dioxide act as powerful greenhouse gases, trapping infrared radiation and insulating the planet. Without these molecules, the planet's surface would be locked in ice under the sun's still weak rays. Instead, the Archean Earth enjoys a balmy heat, its greenhouse effect providing a vital blanket of warmth. The traveler is struck by the delicate balance at play. These gases, though lethal to humans, are essential for maintaining the Earth's early warmth, setting the stage for the gradual emergence of life. As the sun sinks below the horizon, the endless ocean transforms under a star-filled sky. With no continents yet formed, there is no land in sight, only the vast, dark expanse of water. The traveler recalls that the rocks beneath the capsule are slowly forming, built from the grains eroded off submerged volcanic ridges. These are the ancestors of the most ancient rocks that will one day rise to the surface in Western Australia. But for now, they lie hidden in the ocean's depths. The ocean stretches in all directions, a realm of dark, crushing pressure. Though life stirs in the depths, microbial mats of cyanobacteria beginning to harness the sun's energy, their existence is humble and unnoticed in the grand scheme of the planet's evolution. Night brings its own wonders. The sky darkens, and stars blaze brilliantly, unimpeded by the haze that colors the day. The traveler marvels at the vibrant auroras that ripple across the heavens. Unlike the green auroras of modern Earth, these lights are vivid blues and reds, a signature of the nitrogen-rich, oxygen-poor atmosphere. Curtains of light cascade across the sky, a celestial dance that hints at the energetic forces shaping the planet. The endless ocean and the unbreathable atmosphere weigh heavily on the traveler. While the warm waters lap soothingly against the capsule, they cannot escape the realization that this world is still far from hospitable. The beginnings of life are stirring, but it remains a minor player in the planet's story. For all its potential, the Archean Earth is not a place they can stay. Adjusting the controls, the traveler sets their sights on a new era. Somewhere in the billions of years ahead, the air will change, continents will rise, and life will flourish. As the time machine hums to life, the traveler takes one last look at the serene but alien ocean before disappearing into the stream of time, chasing a future where survival might finally be possible. The traveler adjusts the dials of the time machine and prepares for another leap, this time to a transformative period in Earth's history, the Paleoproterozoic era. Targeting the era of the Great Oxidation event some 2.4 billion years ago, they reflect on the incredible parallels between the Perseverance rover's MOXIE experiment and the natural processes that began reshaping Earth's environment billions of years earlier. With a hum of energy, the capsule begins its descent into the past, racing back toward the time when life fundamentally altered the planet's atmosphere. As the time machine settles into its destination, the traveler surveys the primitive Earth. The planet is still starkly alien. There are no forests, no animals, and no land-dwelling organisms of any kind. Instead, the surface is dominated by lifeless rocks and endless, shallow oceans. The air, thick with volcanic gases, is a stifling mix of nitrogen, methane, and carbon dioxide, but crucially, no oxygen. For nearly 2 billion years, life has clung to the deep ocean's thermal vents, thriving in isolated pockets where heat and minerals provide the necessary energy for survival. These chemotrophic microbes build intricate layered communities, known to modern scientists as stromatolites. These structures consist of stacked microbial mats, where each layer relies on the metabolic byproducts of the one below, creating a primitive but efficient ecosystem. However, their reach is limited. These life forms cannot expand beyond the narrow, energy-rich zones of volcanic activity. Then, a revolutionary innovation changes everything. Deep in the sunlit waters, certain microbes evolve pigments that enable them to capture sunlight. This evolutionary breakthrough gives rise to photosynthesis, allowing microbes to harness the sun's energy directly. These pioneering organisms, the ancestors of cyanobacteria, transform the abundant carbon dioxide in the atmosphere and water in the oceans into energy-rich sugars. The byproduct of this reaction is a gas that will become central to life's future on Earth: oxygen. As photosynthetic microbes spread across Earth's shallow oceans, they begin pumping oxygen into the water, a feat as monumental as any technological advancement in human history. For the first time, Earth's oceans and atmosphere are enriched with this reactive gas. At first, the oxygen quickly bonds with dissolved iron in the oceans, forming rusty deposits that sink to the sea floor. Over millions of years, these reactions create the banded iron formations found in ancient rocks today. Valuable clues to this transformative period. Eventually, the oceans become saturated with oxygen, and it begins to escape into the atmosphere. This marks the dawn of the Great Oxidation event. The traveler watches as the planet's air slowly transitions, the skies losing their earlier hazy orange tint as oxygen accumulates. The oxygen doesn't just change the composition of the atmosphere, it transforms the planet itself. Oxygen is a highly reactive gas, and its introduction triggers a cascade of chemical reactions across Earth's surface. Rocks are oxidized, creating the red, rusty hue seen in ancient soils. Methane, a potent greenhouse gas that has long warmed the planet, reacts with oxygen, causing a dramatic cooling effect. The planet teeters on the edge of its first major ice age. The sudden presence of oxygen is both a blessing and a curse. While it enables more efficient metabolisms and paves the way for the evolution of complex life, it is toxic to many of the anaerobic organisms that once dominated Earth's biosphere. For these life forms, oxygen is a deadly poison. Many are driven to extinction, while others retreat to oxygen-free niches, such as deep sediments or the guts of future multicellular organisms. This great die-off is one of the first mass extinctions in Earth's history. At the same time, the stage is set for life's next great leap forward. Oxygen opens up new possibilities for metabolism, enabling the evolution of larger, more complex organisms. In time, the oxygen-rich atmosphere will also form a protective ozone layer, shielding the surface from harmful ultraviolet radiation and allowing life to venture onto land. Inside the safety of the capsule, the traveler marvels at the unfolding drama outside. The transformation of Earth's atmosphere by these ancient microbes is not unlike the MOXIE experiment on Mars, albeit on a far grander scale. What took humans decades of research and engineering to achieve, extracting oxygen from an alien environment, these microbes accomplished through the blind ingenuity of evolution. The traveler records their observations, realizing that this singular event, the Great Oxidation, is the foundation for all complex life, including their own. Without this natural feat of terraforming, Earth might have remained a planet dominated by microbial mats and methane haze. The realization is humbling. As the time machine's controls hum to life again, the traveler sets a new target date. Their journey through Earth's past is far from over, But they now understand more deeply how the simplest organisms can leave the most profound legacy. Oxygen, once a byproduct of microbial life, will become the breath of civilizations yet to come. As the traveler peers out of the time machine's frost-rimmed windows, a slow but perceptible transformation begins to take shape across the frozen expanse. The icy world of the Huronian glaciation is gradually giving way to more dynamic and colorful landscapes. It is now 2.2 billion years ago, and the traveler observes the first signs of geological rejuvenation. As mountains are thrust skyward, their jagged peaks painted in hues of iron-rich red, while vast ice sheets retreat in fits and starts. Erosion and weathering smooth the newly formed ridges, depositing sediments into the shallow seas that are finally beginning to thaw. The thawing of Snowball Earth was not a sudden event. Over hundreds of millions of years, the Earth's internal forces pushed against the icy grip of glaciation. Volcanoes, impervious to the cold above, erupted with force, spewing vast quantities of carbon dioxide into the atmosphere. With less methane to react with and bind it into other compounds, this carbon dioxide began to accumulate. Slowly but surely, the greenhouse effect resumed its work, trapping the sun's faint heat and warming the planet. The traveler marvels at the evolving atmosphere, watching the readouts in their capsule as the composition of gases fluctuates. The percentage of carbon dioxide rises, nudging global temperatures upward. Ice sheets crack and fracture, exposing dark land masses that absorb sunlight and amplify the warming process. Meanwhile, photosynthesizing microbes continue their relentless production of oxygen. Although this waste product had previously contributed to global cooling by depleting greenhouse gases, it now begins to accumulate more steadily in the atmosphere. The traveler notes with interest the way oxygen levels oscillate, rising and falling with the cycles of life and extinction that continue in the shallow seas. This plateau, the traveler realizes, is a prelude to something greater. While oxygen levels are still not high enough to breathe, the slow increase suggests that life is finding new ways to adapt and thrive. The traveler reflects on the irony. The same process that led to the catastrophic Huronian glaciation is now driving the conditions for its eventual end. The oxygenation of the atmosphere is not only a byproduct of photosynthesis, but a herald of Earth's next great chapter. Outside the time machine, the traveler sees the transformation accelerate. Where once there was only ice, shallow seas now sparkle under the dim light of the young sun. The retreating glaciers expose vast stretches of rocky ground, which are soon covered in sediments, washed down by rivers fed by melting ice. Layers of sandstone and shale begin to build, and the first signs of complex sedimentary structures appear. The Earth's surface takes on a rusty hue as iron-rich rocks oxidize in response to the increasing presence of atmospheric oxygen. This red coloration, the traveler knows, will one day be found in ancient banded iron formations, preserved as evidence of this transformative era. Despite the thaw and the beauty of the unfolding landscape, the traveler remains acutely aware of their own predicament. The capsule's instruments confirm what the traveler already suspects. The air outside is still unbreathable. Oxygen levels hover around 5%, tantalizingly close, but still far too low to support anything more than microbial life. Frustrated but undeterred, the traveler contemplates their next move. Should they push further forward in time, risking another ice age or cataclysm? Or should they linger here, trying to better understand the slow, rhythmic dance of life and geology that is sculpting this ancient world? As they consider their options, the traveler notices something remarkable in the data being collected. The oceans, once lifeless except for the simplest of microbes, are now beginning to teem with more complex forms of life. While still microscopic, these early eukaryotic cells, with their nuclei and organelles, represent a significant leap forward in evolution. This is a sign that Earth's biosphere is on the cusp of diversification, laying the groundwork for the incredible explosion of life yet to come. The traveler decides to take one last look at this Paleoproterozoic world before setting a new target. They step back from the controls, letting the time machine idle as they record their observations. The journey so far has been harrowing, but it has also revealed the resilience of life and the delicate balance of planetary processes. With a deep breath, they reach for the controls once more. The great oxidation event has set the stage, but the traveler knows that the true story of life's emergence is only just beginning. They set their sights on a time when the Earth's atmosphere might finally be ready to support more than just microbes, hoping that their next leap will bring them closer to the vibrant, living world they seek. The traveler steadies themselves on the rocky ground, their boots crunching against the gravelly surface. Each breath is a reminder of how far they've come. Through epochs of barren desolation, suffocating atmospheres, and endless oceans devoid of visible life. Now, at last, they stand under a sky filled with breathable air, on a planet visibly teeming with potential. It feels surreal to touch the ground and see the hints of greenery staining the shoreline, knowing this was once an unimaginable future for Earth. The traveler gazes out at the sprawling shoreline. The waters shimmer under a pale sun, reflecting a mix of blue and green that seems alive with microbial activity. This isn't the vibrant, bustling planet they left behind in the modern era, but it's a marked improvement from the blackened seas and sulfurous skies of the boring billion. The air feels slightly heavier than they're used to, humid and warm, with the faint tang of salt and a subtle edge of organic decay. The smell is reminiscent of a tidal flat after the retreating tide, a medley of life and death in the making. The rocks beneath their feet bear the unmistakable signs of life's growing foothold on land. Delicate algal mats have spread across the damp surfaces, creating a slimy green film that glistens in the sunlight. These primitive photosynthesizers are pioneers, laying the groundwork for ecosystems that will one day dominate the planet. The traveler marvels at the resilience of these early colonizers, their ability to withstand the harsh UV radiation from the sun and the relentless battering of tides. They are reminded of the fossilized traces they studied back home, ripples and wrinkles left by organisms just like these, frozen in stone as a testament to this critical chapter in Earth's history. The traveler's attention is drawn back to the capsule, where the atmospheric monitor displays a reading they've been hoping to see for eons, nearly 20% oxygen. This concentration, coupled with a drop in methane and hydrogen sulfide, marks a turning point in Earth's atmospheric evolution. For the first time in billions of years, the atmosphere has reached a state capable of supporting more complex life forms. This is the Neoproterozoic Earth, primed for the dramatic evolutionary leaps yet to come. The rise in oxygen has been driven by the incredible efficiency of photosynthesis, which has finally reached a global scale. Cyanobacteria, algae, and other photosynthesizing organisms have proliferated across the oceans, releasing oxygen into the atmosphere in unprecedented quantities. This oxygen revolution is transforming not only the air, but also the chemistry of the oceans. Iron and other minerals, once dissolved in the water, are oxidizing and settling out, creating deposits that will be studied by future geologists as banded iron formations. Carefully pacing themselves to avoid overexertion, the traveler ventures further from the capsule. Each step feels like a leap through time, a connection to the earliest days of multicellular life. In the shallows of the shoreline, they spot something extraordinary: clusters of larger, more complex organisms. These are not yet animals, but colonies of cells working together, sharing resources and signaling to one another in ways that hint at the first steps toward true multicellularity. Kneeling by the water, the traveler examines the gelatinous masses. These simple organisms may look unassuming, but they represent a revolution in evolution. Cooperation between cells is a game changer, enabling specialization and paving the way for the diversity of life that will eventually populate the Earth. They feel a swell of wonder and gratitude, knowing that these humble beginnings will one day lead to everything from towering redwoods to leaping gazelles and even themselves. Despite the progress, the traveler knows this is just the beginning of the Neoproterozoic. Ahead lies a world-changing event, the cryogenian glaciations, where the Earth will once again freeze over in a dramatic Snowball Earth episode. But unlike the deep freeze of the Huronian, this one will set the stage for the Cambrian explosion, a burst of biodiversity that will forever alter the trajectory of life on Earth. For now, the traveler chooses to linger, absorbing every detail of this transformative era. They are surrounded by a world on the cusp of change, a planet where the groundwork for all future life is being painstakingly laid. As they breathe in the ancient air, rich with the history of Earth's struggle and triumph, they feel an overwhelming connection to the past and an unshakable curiosity for what lies ahead. Standing at the edge of a primordial sea, the traveler gazes out at a horizon that holds both the memories of Earth's distant past and the promise of its astonishing future. This is a moment to savor, a rare pause in the relentless march of time, a snapshot of a world becoming something new. The time-traveling paleontologist sits back in their seat, letting the rhythm of the machine's movement and the blur of passing millennia guide their thoughts. Ada Blackjack's incredible story of resilience echoes in their mind, a testament to human ingenuity and survival instincts in the harshest of conditions. But as the paleontologist considers their own position, Ada's challenges pale in comparison. At least she had a breathable atmosphere, food to hunt, and water to drink. The paleontologist faces a more fundamental problem. Earth itself has not yet become fully habitable for humans. For a human to survive anywhere, certain elements are non-negotiable. Oxygen is the first and most obvious requirement. Without it, no amount of ingenuity, adaptability, or technology can sustain life. Thankfully, the traveler has finally reached a point in Earth's history where oxygen is plentiful enough to breathe. The next hurdle is temperature. The human body can only function within a relatively narrow range of temperatures. Too cold, and metabolic processes slow to a dangerous crawl. Too hot, and dehydration and heat stroke become lethal. Water is the next essential. Though the Earth's oceans have existed for billions of years, not all water is safe to drink. Early oceans were acidic, salty, and filled with dissolved minerals and organic compounds that could wreak havoc on human physiology. Even now, standing at the edge of a Neoproterozoic ocean, the paleontologist knows the water is likely unfit for human consumption. Finally, there is food. perhaps the most complex necessity of all. Early Earth's ecosystems were dominated by single-celled organisms, algae, and primitive plants. Without advanced digestive systems capable of breaking down cellulose or other tough organic compounds, humans cannot derive much nutrition from these early life forms. Moreover, the absence of large, protein-rich animals or edible seeds means the traveler would need to invent entirely new methods of sustenance to survive in this alien time. As the paleontologist reflects, they realize that survival is not just about meeting the basic needs of air, water, and food, it's also about adaptability. Earth's environments are in constant flux. Even now, as they traverse the Neoproterozoic, the traveler is aware of the storm building over the ocean, a reminder that the planet's volatile weather can turn hospitable conditions into death traps in an instant. Unlike Ada Blackjack, who had the stability of a single location to adapt to, the traveler must contend with a dynamic planet where continents drift, climates shift, and ecosystems evolve. The thought is daunting, but it also sparks a new sense of curiosity. What if humans could follow these changes, learning to adapt to Earth's evolving environments over geological time? The traveler's musings turn practical. How could they, or anyone, survive in the deep past of Earth? A few ideas begin to take shape. The first is mobility. Like early human nomads, the traveler realizes they must stay on the move, following habitable conditions wherever they emerge. The time machine, it seems, is their ultimate survival tool, providing not only shelter, but the ability to escape uninhabitable conditions entirely. Second, they consider technology. Modern humans have long relied on tools to bridge the gap between natural limitations and environmental demands. Could the traveler create filters to purify water, harness solar energy to generate heat or electricity, or even cultivate edible microorganisms to produce food? The possibilities are tantalizing, but also intimidating. Without the resources of their own era, even the simplest tools would require immense ingenuity to manufacture. Lastly, the traveler thinks about community. Human survival has always been a collective effort. The thought of returning to the past with a team of specialists, engineers, biologists, and survivalists is an appealing one. Together, they could pool their knowledge and skills to tackle the challenges of deep time. As the storm on the horizon begins to encroach, the traveler feels a pang of unease. The time machine, sturdy as it is, may not withstand the full fury of the Neoproterozoic weather. Reluctantly, they retreat back into the capsule, sealing themselves inside just as the first gusts of wind whip across the beach. From the safety of the pod, the paleontologist watches as sheets of rain lash the shore, reducing the verdant algae mats to a churned mess of foam and muck. It's a stark reminder that even in this relatively habitable era, Earth is far from a comfortable home. And yet, there is a strange beauty in its rawness, in the untamed power of nature as it shapes the planet for the life forms yet to come. The paleontologist's journey is far from over. They still hope to find a time when Earth can fully support human life. But they are beginning to realize that survival in deep time is not just a matter of meeting basic needs. It's about understanding and respecting the planet's natural rhythms, about finding a balance between adaptation and innovation, and about appreciating the resilience of life in all its forms. With a final glance at the storm-racked landscape, the traveler adjusts the controls and sets a new destination. The past holds many more secrets, and they are determined to uncover them all. After all, survival isn't just about enduring. It's about thriving, learning, and pushing the boundaries of what's possible. Charles Doolittle Walcott's discovery in the Burgess Shale marks one of the most significant fossil finds in history, providing a window into a world teeming with life from over 500 million years ago. The Burgess Shale, located high in the Canadian Rockies, preserves creatures from the Cambrian explosion, a period of unparalleled evolutionary innovation that followed the Ediacaran era. This discovery revealed not just the diversity of life, but also the complexity of ecosystems that had emerged. A testament to the Earth's capacity for dramatic biological change. The paleontologist aboard the time machine has now resolved to witness this explosion of life firsthand. After leaving behind the strange quilted bodies of the Ediacaran biota, they adjust the dials to leap forward just a few million years to the early Cambrian. What greets them is a world transformed. The air, warmed by an increasingly bright sun and enriched with oxygen, is now far closer to breathable. Shallow seas stretch out in all directions, teeming with activity and energy that is immediately visible even from within the capsule. Upon stepping out onto the shore, the traveler is struck by the vibrant hues of this new world. The clear, shallow waters reveal creatures of every size and shape, darting, scuttling, and drifting along the seabed. Schools of tiny, shrimp-like animals flash silver as they move in synchrony, while larger, segmented creatures plow furrows into the sand. The paleontologist marvels at the sight of trilobites, armored, many-legged arthropods, crawling across the ocean floor in organized lines, their segmented bodies glinting in the sunlight. Kneeling at the water's edge, the traveler is captivated by a scene of predation. A sleek predator, Anomalocaris, with its large, grasping appendages, swoops down to snatch a smaller, shelled creature. This marks a striking difference from the passive Ediacaran fauna. Here, competition and aggression define survival, and the ecosystem pulses with an energy that is both thrilling and unnerving. As the traveler surveys this thriving ecosystem, they reflect on the role of fossil preservation in revealing such ancient secrets. The Burgess Shale owes its exceptional preservation to a unique set of geological conditions. The animals that lived in these Cambrian seas were buried quickly in fine sediment during underwater landslides, which prevented decay and scavenging. Over millions of years, the mud compressed into shale, encasing the delicate soft tissues of creatures that would otherwise have vanished without a trace. It's this remarkable preservation that allowed Walcott and later scientists to reconstruct a vivid picture of life in the Cambrian. Here were creatures unlike anything alive today: Hallucigenia, with its spiky legs and worm-like body; Opabinia, with 5 eyes and a flexible proboscis; and Pikaia, an early chordate that offers a glimpse of the evolutionary lineage leading to vertebrates. For the paleontologist, the Cambrian offers a world far more hospitable than the barren Ediacaran. Food is abundant. Trilobites, small mollusks, and other soft-bodied creatures could easily provide sustenance. The shallow coastal environment also offers natural shelter in the form of rocky overhangs and tidal pools. With simple tools and ingenuity, this era could sustain human survival, though the traveler acknowledges the ethical quandary of interfering with such a delicate and ancient ecosystem. Looking deeper into the tidal pools, the traveler is drawn to the translucent forms of jellyfish-like creatures drifting near the surface. Unlike the rubbery Ediacaran biota, these animals are mobile and seemingly more aware of their surroundings. Crustacean-like creatures scuttle along the seabed, using their specialized appendages to dig into the mud for food. The traveler begins collecting samples, shell fragments, small mollusks, and pieces of kelp-like algae for closer examination back in the capsule. But as they work, they're reminded of the fleeting nature of this moment in Earth's history. Just as the Ediacaran biota gave way to the Cambrian explosion, so too will these creatures evolve or vanish over the millennia to come. Before returning to the time machine, the traveler pauses to take in the scene one last time. The Cambrian is a period of abundance and innovation, but it's also a reminder of life's fragility. Mass extinctions are an inevitable part of Earth's history. And even the most successful species are not immune to environmental change. As the paleontologist sets the dials for their next destination, they are filled with a profound sense of gratitude for the interconnected web of life that has endured through eons of upheaval. The Cambrian explosion is more than just a chapter in Earth's history. It is a testament to the resilience and creativity of life itself. A burst of evolutionary brilliance that paved the way for everything that followed. The traveler marvels at the transformation of the Earth's surface over these eons, witnessing the steady march of life from the shallow seas onto land and the profound changes it brings. As they move through the Devonian period, they see the rise of the first true forests. Towering ferns and tree-like plants, such as Archaeopteris, dominate the landscape, their deep roots stabilizing the soil and creating vast networks of nutrient-rich sediment. These primitive trees are not only reshaping the terrain, but also altering the atmosphere, drawing down carbon dioxide and contributing to the creation of a more temperate climate. The Devonian is also known as the Age of Fishes, and the traveler is drawn back to the water's edge to see this new explosion of biodiversity. The oceans teem with armored placoderms, such as the formidable Dunkleosteus, a predator equipped with sharp, slicing jaw plates. Smaller bony fish dart among the shallows, while early sharks patrol the deeper waters. Coral reefs, complex and sprawling, provide shelter for a host of marine organisms. Life has diversified in remarkable ways, building ecosystems that are more intricate and interdependent than ever before. On land, the traveler notices the first appearances of creatures venturing beyond the water. Early tetrapods, like Tiktaalik, are experimenting with life at the water's edge. These pioneering animals, with their limb-like fins, are the first steps in the evolution of vertebrates that can fully inhabit terrestrial environments. The traveler imagines these creatures awkwardly dragging themselves onto muddy banks, their adaptations paving the way for future terrestrial dominance. Continuing forward, the time machine slows at the Carboniferous period, roughly 300 million years ago. Here, the world is a lush green paradise dominated by vast swampy forests. Giant lycophytes and horsetails grow in dense thickets, their trunks rising to impressive heights. The humid climate fuels explosive plant growth, creating extensive coal-forming forests that will later give this period its name. The traveler steps out into this steamy, oxygen-rich world and feels an immediate difference. The atmosphere, now composed of nearly 30% oxygen, allows for the evolution of massive insects. Dragonflies the size of seagulls, such as Meganeura, glide gracefully through the air, while millipedes like Arthropleura stretch to lengths of up to 2 meters, crawling through the dense undergrowth. The traveler is both awed and unsettled by these gargantuan arthropods, marveling at the evolutionary possibilities of this high-oxygen environment. The swampy terrain, while teeming with life, presents challenges for survival. The traveler reflects on the lack of large animals to hunt for sustenance, as the dominant vertebrates are still amphibians confined to water or damp habitats. Building shelter in this waterlogged environment would also be difficult, as much of the wood is water-saturated and prone to decay. Despite its verdant beauty, the Carboniferous presents formidable challenges to long-term human habitation. Knowing the story of life's relentless march forward, the traveler prepares to leap into the future once again. Eager to see how these early forests and giant insects will give way to new forms of life and ecosystems. They adjust the dials, setting their sights on the next great chapter of Earth's history, the age of reptiles and the dominance of the dinosaurs. Emerging from the dense gymnosperm forests of the Carboniferous and into the vibrant, flower-filled landscapes of the late Mesozoic, the traveler finds themselves in a transformed world. It is the middle of the Cretaceous period, roughly 120 million years ago, and the once monotonous greenery of conifers has been replaced by a riot of colors and scents. Angiosperms, or flowering plants, have taken root across the land, introducing a revolutionary new approach to reproduction and survival. These plants have evolved flowers to attract pollinators and fruits to entice animals, who in turn spread their seeds far and wide. For the traveler, this evolutionary leap represents something more immediate: a wealth of accessible and nutritious food. The fruits hanging from trees and vines are soft, sweet, and bursting with the carbohydrates and vitamins needed to sustain. After eons of subsisting on undigestible algae or protein-rich but nutritionally incomplete marine life, the traveler can now enjoy a balanced diet. In addition to the fruits, flowering plants have brought other gifts to this ancient ecosystem. Grains and seeds, precursors to staples like wheat, rice, and corn, are beginning to take shape in the plant world, though they remain a distant promise of the agricultural revolutions to come. The traveler gathers and samples what they can, reveling in the newfound abundance of food options that offer both energy and nourishment. Around them, the Cretaceous landscape teems with life. Birds like Geolornis flit between the branches, feasting on the same fruits as the traveler. Their sleek forms and colorful feathers suggest an advanced stage in avian evolution, and their behaviors hint at a deepening partnership with the flowering plants they help pollinate and propagate. Larger animals roam the plains and forests too, including dinosaurs that coexist alongside this rapidly diversifying flora. The traveler observes herbivorous dinosaurs grazing among the plants, their diets now enriched by the tender leaves and fruits of angiosperms. Meanwhile, predators like Tyrannosaurus rex lurk in the shadows, their sharp senses attuned to the movements of these plant-eating giants. The ecosystems of the Cretaceous are more complex and interconnected than anything the traveler has seen before, with flowering plants at the heart of this evolutionary web. The traveler is struck by how these plants have not only reshaped the land, but also influenced the behavior and evolution of animals. The co-evolutionary relationship between flowering plants and their pollinators, or seed dispersers, demonstrates nature's intricate balance and the power of mutual adaptation. It is a reminder of the interdependence that underpins all life on Earth. As the traveler moves through this lush environment, they note how the angiosperms have also begun to change the climate. by drawing down carbon dioxide through photosynthesis and stabilizing soils with their roots. These plants contribute to the regulation of Earth's atmosphere. The air is fresher, the climate more temperate, and the landscapes more inviting than ever before. For the first time in their journey through Earth's history, the traveler feels a sense of home. They find shade under the broad leaves of a flowering tree, savoring a piece of fruit and gazing out over the vibrant, thriving ecosystem. It is a world on the brink of modernity, laying the foundation for the habitats and resources that humans will one day rely on. Though their time in the Cretaceous is limited, the traveler knows that the seeds of the future have been planted, both figuratively and literally. The angiosperms that now dominate the landscape will continue to diversify and spread, shaping the course of evolution and creating the conditions for the rise of mammals, primates, and eventually humans. And with that thought, they prepare to make their next leap forward, eager to see the culmination of Earth's long and extraordinary story. Belonging to the angiosperms, flowering plants, these ancient flora revolutionized the ecosystems of Earth with their seeds encased in fleshy ovaries. These modifications evolved in an astonishing variety of forms, designed to attract animals and ensure successful dispersion and germination. For humans, these fleshy fruits and carbohydrate-rich parts of angiosperms became a vital, digestible food source. Unlike the tough, nutrient-scarce gymnosperms that had dominated earlier eras. Though their fossil record dates their emergence to roughly 140 million years ago in the early Cretaceous, angiosperms quickly rose to prominence. By 120 million years ago, as the fossilized diet of Geological suggests, these plants had cemented their role in the food web. This flourishing world of angiosperms is where the traveler finally finds themselves. Their time machine, silent and coated in a fine layer of dust, sits quietly in the shade of towering ancestral trees. Its display reads the late Mesozoic, a time when dinosaurs roamed the Earth in unparalleled diversity. The land is alive with activity. Frilled triceratops graze in herds, ankylosaurs lumber heavily through the undergrowth, and small mammals scurry from burrows, wary of the theropod predators lurking in the shadows. Primitive birds, like Geological, dart between branches, gathering fruits and seeds from the flowering plants that have reshaped this landscape. Among these ancient beings, the time traveler, now fully adapted to this world, gathers their daily sustenance. The angiosperm fruits, rich in carbohydrates and flavor, complement their diet of seafood and meat, which they have honed the skills to catch and prepare. The traveler has also built a simple but secure shelter at the forest's edge, where the plains stretch out, dotted with the majestic figures of herbivorous dinosaurs. Here, for the first time since beginning their journey through time, they have all the essentials for survival: food, water, breathable air, a comfortable temperature, and adequate shelter. Looking back on their journey, the traveler reflects on the long and arduous path that brought them here. They first encountered water in the Archan, but it was uninhabitable. Breathable air emerged only billions of years later during the Neoproterozoic. They found protein in the Cambrian seas, but lacked balance in their diet. True shelter only became possible in the Carboniferous, when towering plants created shaded havens. And yet, it wasn't until the mid-Cretaceous, just 100 million years ago, that all the elements of survival came together in one place and time. The traveler considers the paradox of their experience. The Earth has always been a planet teeming with potential. Yet it took billions of years of evolution and planetary change to create a world where a human could thrive. Is it a testament to the fragility of modern humans, so finely tuned to the environments of their own time? Or is it a reflection of the dramatic, ever-changing nature of Earth itself? Perhaps it is both. For now, these questions can wait. The traveler, no longer a mere observer, but a part of this ancient world, embraces their role as a settler in this prehistoric paradise. With every breath of oxygen-rich air, every bite of sweet fruit, and every night spent under the Cretaceous stars, they live a life of unparalleled connection to Earth's extraordinary history. And so, the journey ends here, in a land of dinosaurs and flowering plants, in a time both ancient and vibrant. This is the earliest point in Earth's history where a human could survive and thrive. And for the traveler, it is home. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.